Okay, so just say so. Okay, everyone can hear. Tell me if you can't. So I tried to make this the level of this. I know there are people of different levels and different backgrounds. So it's if you're. I tried to aim it at say graduate students, as long as with some knowledge of holomorphic forms and mass forms. Okay, so I'm going to start. I'm going to go quite slowly. And the other thing is. I don't know how familiar people are with homology. So I'll try to, by and large, stick to the simplest case where I don't have to make any use of it. Okay, so let me start for a while with SL2Z, and then we'll. So for the first half an hour or so, I'll just get to the question which we're going to discuss for the rest of the series. Okay, so first, just some simple notation. If gamma is a group, we can, gamma ab means for us the abelianization of gamma. Okay, in other words, that's the largest abelian quotient of gamma, so it's the quotient of gamma by all. So you take gamma quotiented by the subgroup generated by all elements x, y, x inverse, y inverse, where x and y are in gamma. Okay. So what we're going to be talking about is what happens when we do this to groups like SL2 over an imaginary quadratic field. Right. So if gamma comes with a presentation, this is very easy to compute. So, for example, if you happen to be given a presentation, let's say it's something like is generated by two elements, subject to the. I'm just making this example at random. Beta to the 5 is the identity. Then, so the abelianization will be. So it will have two generators, so z squared, and then you quotient by relations which come from this. So in this case, you quotient by the row vectors 2, 3, and 4, 5. Okay, and I guess that's the group Z mod 2. Okay. All right, so what I'll start by doing is we'll do this for subgroups of SL2Z, and I'll explain why you might be interested in doing that from the point of view of holomorphic modular forms. And then, so what I'm going to talk about is, so we'll discuss this gamma ab first for subgroups of SL2Z, and then after we do that, then I'll make this z into a z square root d. And we'll see how the situation changes. Okay, so right, so I'll stick to the usual. It doesn't really matter which family of subgroups we choose, but I'll stick to the standard ones that we talk about in number theory. So gamma naught of n will just as usual be the elements a, b, c, d in SL2Z. That is determinant 1. So determinant is 1, and n divides c. Okay, and in a second, the same definition also makes sense. So right now, a, b, c, d are integers, but this also makes sense if we did z square root 2. Okay. Okay, so what happens for subgroups of SL2Z first? Okay, so for for subgroups of SL2Z, this is what happens when you abelianize. This is very closely related to weight 2 modular forms. So gamma, if you take this and you take its abelianization, what you get, so I'm not going to prove this, but I'll say in a second where it comes from, is you get, actually, I guess the statement I'm about to make is literally right only when n is prime. But all right, so it's z to the 2h plus 1 plus a small, in a sense I'll say, small finite group, and where h is going to be the dimension of the space S2 of n. So this means weight. So weight 2 level n holomorphic cusp forms. Holomorphic cusp forms. Okay, so I'm going to assume people are familiar with that definition. All right, when I say a small finite group, in this case, what it means is that every element has order at most 6. Okay, so it really is very small, but in particular, it's at most 6 torsion. All right, so I want to explain where this comes from because this maybe gives you some motivation about why you would be doing this abelianization thing in the first place. Okay, so the point is that in fact this is very closely related to the space of weight 2 forms, and if you didn't know the definition of a weight 2 form, you would notice many of the same things if you were studying this. So I'll kind of explain where this relationship comes from. So in fact, are there any questions? Just shout out if there are questions. It's because there. So this relationship between these comes from there is a pairing. Okay, a bilinear pairing. Let me say, bilinear pairing. All right, this plus 1, as I said, it's right if n is prime, and this has to do with Eisenstein series. Okay, so it's a little bit of a, if n is not prime, it's plus something a bit bigger. But anyway, I'm going to sort of not worry too much about it. There's a bilinear pairing. So if you have from this to the complex numbers, and I'll define it for you. So given an element, let's call it gamma bar in this abelianization. Okay, so this is an abelianization, so it comes from some element gamma, so the image of some gamma in the actual group. The way you define the pairing is you just integrate the form. So gamma, and you have a form f in here. You define this to be the integral from w0, w gamma w f of z dz. Okay, here w is any element of the upper half plane. So this integral is independent of the choice of w. Okay, so you could. So this means you take any path from w to gamma w. It doesn't matter which. The integral is independent. You take any w, any path from w to gamma w, and integrate this, and this gives you a complex number. Okay, and so this gives you a kind of. And in fact, except for this annoying plus 1, this is actually a perfect pairing. So that means, in fact, we can take a basis, let's say gamma 1. I'm just going to write this very explicitly. Gamma 1 up to there's a basis for this. Oh, let me put the bars for this z to the. Okay. So such that these gamma 1, if just the functionals you get from them, or at least the first 2H of them, gives a basis for the dual to the space of cusp forms. Okay. Now something a bit strange about this is cusp form. This is H-dimensional. It's an H-dimensional complex vector space. So this dual space is also H-dimensional. This is an H-dimensional complex vector space. But this actually gives a real basis. Okay, it gives a basis. So this is H-dimensional over C, but it's 2H dimensional over R. Okay, so that's where the 2 comes from. Okay, so this is kind of the reason that you see this 2H here. And
so you pick any 2H of them. You have 2H plus one of them on the top one, and then 2H remains.
I said there you can choose a basis in such a way that this is true. Yeah. Okay. So more, aside from the plus one, this is this pairing is tensored with the reals is perfect. Okay. So a bit. Even more is true. So one can also define the action of the Hecke operators. Define an action of Hecke operators so for every, let's call them T sub m, where m is relatively prime to n, let's say, on this group in a way which is compatible with here, okay, in such a way that if you apply a Hecke operator on one side, it's the same as applying it on the other side. Okay, so what this means is that, in other words, we can recover all of, if you want, everything we want to know about these weight 2 modules together with the action of Hecke operators on them, you can completely recover if you know the same thing about this. Okay, there are these. Now, well, okay, this is the start of a lot of the algebraic theory of modular forms, but why is this useful? For example, this is a very efficient way of actually computing this. Okay, so if you take n is a few hundred and you want to write down what are the weight 2 modular forms of that level, this is actually rather computable because, as I'll mention again later, it's actually very easy to write down things like a presentation for this, which is not how people exactly do it, but so this is computationally useful, and also for example, it tells you things like this is a fact of fairly basic importance. For example, it tells you the eigenvalues of the Hecke operators are algebraic integers. Okay, because if you think solely about holomorphic things, there's no reason why this should be the case. But here, over on this side, these Hecke operators are represented by integer matrices. So they're.
Why you consider weight 2 forms?
Well, if I considered weight, what do you mean?
Why you started from weight 2 s to n? Just don't see the relation. I mean, why 2 matters so much?
Well, so if it were not 2, this, literally speaking, this would no longer be.
Change the measure. Can't you just?
No, I would have to. So there's no problem making an analog of this theory, but instead of the abelianization, I would have to take homology with some twisted coefficient. So it's not a. It's just for. Sorry?
We'll show up later why this is important.
Maybe I don't.
The generalization is straightforward, but probably needing to know, I guess.
No. So all the statements that we make about this, there'll be parallel statements in higher weight, which would be, the only difference is they're more annoying to formulate because instead of this, I would have to write the homology of this group with coefficients in something, and I was hoping to avoid that.
So you mentioned the 2h plus 1. 1 is for Eisenstein.
One is for Eisenstein series, so it would be more.
2 Eisenstein series, n is prime.
Yeah, that's true. But so, for example, even for n is 1, so you lose 1. Yeah. I don't think we really want to go there. Yeah. Yeah, but in fact, you make a good point. At some point, I'll put a permanent disclaimer that I'll make many statements that are exactly correct in the compact case, and just because it's quite. Okay, so this is, so to speak, an introduction of why you might want to do this process of abelianizing it in the first place. Okay, so I say that it has the same information as the space of weight 2 forms, and now I'll do the same thing, but for other, oh, it's gone. All right. Yeah. So now I'll do the same thing, but I want to replace SL2Z by something bigger. Okay. So now we study the same question. Okay, so now, so let's say replacing z by z of square root d, or by any quadratic order. Replacing z by z square root d. Okay, so in other words, let me call O z square root d, and now this definition, as I said, still makes sense, but let me just write it out so we're clear. So gamma naught n is still, it's now determinant 1 matrices in O. Now these are, okay, the determinant is still 1, and now this element n is allowed to belong to O. In fact, n could be an ideal, but just to keep it as similar to the previous case, we'll just take an element, and n divides c. Okay. All right. So let's first take the case where when d is greater than 0. By the way, everything I say in these talks has an analog for any group. Okay, that is to say, if we're talking about GL5 or any, but I'll try as far as possible to stick to SL2 over quadratic fields, just because the statements are clear and I don't have to talk about higher homology groups. Okay, but this is not the analogs of everything I say. There are analogous things to everything I say. Okay. Right. So first, d bigger than 0. So again, I'll state this somewhat imprecisely and then explain it. What you will find if you do exactly the same thing for d bigger than 0. Okay. So for example, so d should be square free. So for example, maybe z of square root 2. Okay. So what you will find if you do this, again, I won't be entirely precise, but is that this is always a small finite abelian group. Okay, so let me not say exactly what small is, but I can again give you some explicit bound. In fact, I can almost compute it in advance, but I can give some very explicit bound on what the size and the order of elements are in terms of n. Okay, so first of all, it never happens in this case that you have these factors of z. Okay, it's always a small finite abelian group. So let me just explain why this case behaves so differently to z. Okay, so the main reason that this behaves so differently is that there are units. Okay, so it is forced to be small because O has many units. All right, so I just say, so when you form this commutator group, you quotient by elements x, y, x inverse, y inverse. So if U is a unit, okay, so maybe 1 plus square root 2, and you take x to be the element U inverse 0, 0, and y to be the element 1, 1, 0, 1. Am I the only person who's dropped chalk down there? I only see 2 pieces, and I dropped them both. Okay, so if we take this, then x, y, x inverse, y inverse is 1, 1, u squared minus 1, 0. Okay, so it might not be immediately clear why it's useful. Usually when you take this commutator of 2 matrices, you get a giant mess, okay? But if you have units, you can use it to produce a very simple class of elements of this type. And then you can try to check that where did I put the definition, that they generate a large subgroup. Okay, so basically you can use this fact to sort of force this abelianization to be small. Now, from some point of view, that's a little bit disappointing, but you can recover an analog of the theory above. So one can recover an analog of theory for Z if we replace this abelianization. So rather than work with the abelianization, there's another way to talk about abelianization, which is as the first homology group. So I'll briefly talk about homology, but it's not necessary. It's just a passing comment about how we generalize this. So instead of this, we work with the second homology, also called the Schur multiplier. Okay, if you were to work with this, you would see something very parallel to this, where S2 of n will now be replaced by I'll write 2 of n. If you work over a real quadratic field, you can talk about holomorphic forms with 2 different weights, one for each of the real embeddings. So there'll be a very parallel story with a pairing and so forth, but with these kind of what is sometimes called parallel weight 2. And here again, as before, there's a corresponding story for any weights, as long as they're both 2 or larger. Okay, weight 1 is a completely different story. Anyway, so if one wants to generalize the things we're talking about, one needs to make this kind of substitution. But okay, we don't have to do it for. It turns out we won't have to do it for Bianchi groups. So, all right. So now let's take d less than 0. Okay, so for example, z of I. Z of I. And here we find actually, so I'll give you some. Yeah, so here these analogous groups are called Bianchi groups. And so this is, sorry, something called Bianchi groups, or at least maybe, well, maybe this term is usually used for just SL2 of O, but is called so these were called because they were studied by Bianchi, and these are very pretty. They act on just as they act on hyperbolic 3 space, and I'll describe this action later when I need to say more about it. But so they're very parallel to the SL2Z, which acts on hyperbolic 2 space. Okay, and Bianchi actually used the geometry of these actions. So this is more than 100 years ago. He already figured out fundamental domains for these actions, and for certain small values of d, he essentially computed presentations for these groups. Okay, so Bianchi did quite a lot already. Anyway, here what we find a phenomenon that's quite different. So now there are no units, and now it turns out that gamma naught of n ab can be quite large. All right, so let me write some data related to this, and then we'll. So yeah. Okay. Are there any questions? Okay, so I'm going to give you some data that was computed by Haluk Sengun. And it was computed in response to a conjecture that Nicolas Bergeron and I made. And I'll say the conjecture in a moment, but let me show you the data first. And that's, OK, so this is for O is Z of I. And I believe that this data is actually not for SL2, but for PSL2. Okay, but OK, so here we go. For n is 9 plus 4i, this abelianization is Z mod 5 plus Z mod 3 plus Z mod 2 to the 6. Okay. For n is, OK, sorry, I'm just going to pick this up so I can transpose it here. For n is 41. So here it's Z mod 4078793513671 Z plus Z mod 292306033 Z plus Z mod 220. Oh, OK. Let's stop there. It goes on actually. You probably don't want to see another version of that, but let's. I'll just to abbreviate. If you go up a little bit higher, the same thing because Z. So it can Z plus T, where T is a finite group. T is finite of order. Its order is bigger than 10 to the 310. Okay, so unless you really want to see it. Okay, by the way, the primes and so forth that show up in these are essentially random. Okay, that is, there's no naive, there are no, the sizes of these look more or less like random numbers from a factorization point of view. Okay, so this was actually in this this kind of thing had been computed before, but somehow you only kind of see how this blows up when you go moderately deep. Like to do this computation is not so trivial. Okay, this doesn't look like such a large number, but what's relevant is its square, and then you have to do linear algebra and integer linear algebra, things of that size. So it's not. And so this was his. So he computed this because Nicolas Bergeron and I made the following conjecture. And I conjectured. All right. Again, this is a general conjecture, but I'll specialize to this case. Specialized to here. That that this grows at a very specific rate. So if we take the size of this now, as you see. This could be also have an infinite part. So when I say the size, I just mean the finite part or the torsion part. So what we conjectured is, and I guess maybe I should say that yeah, maybe the constant I'll write is, let's say n varies through primes for this to be. This should converge to lambda over 18 pi, where lambda is this. Okay, so sum of alternating odd squares. Okay, so All right, so this is the in short, it grows exponentially with the absolute value of this number. Okay, but by the way, the agreement with this conjecture is very good. Numerically speaking. So what I want to talk about is more or less discuss some of the things that are around this conjecture. Okay, so in a way, maybe the conjecture itself is not as interesting as some of the things which show up when you start to try to understand what's going on. So, okay, so the goal of the lecture series is to try to get some understanding of what is happening here and what it's related to. Are there any questions? Yeah. What?
Transcendence of numbers given by this kind of alternating systems introduction to. No, it has nothing to do with what you do, but you ask a question.
Yeah.
The size of the torsion subgroup?
Yes, I'm sorry, I said that, but I should have written it. Yes, it is the size of the torsion subgroup. So it absolutely can be infinite, and by far the most interesting phenomena here happen in this case, when it has an infinite part. So that's what I'll sort of head towards. Okay. Yeah, any other questions?
The dots are odd squares.
Those are odd squares, yeah. Yeah, so this number is like...
Is there anything about the rank of the group, free part?
No, the rank of the free part behaves in an extremely irregular way. So it's... are you saying... So certainly... How do you say? The rank of the group is, a lot of the time, is 0. Let's put it that way. It's hard to even make any sensible statement about it because it behaves so irregularly.
The previous two example has 0 free part.
What is that?
The previous two examples, they have 0 free.
No, the first one doesn't have zero free part.
These two, the last two.
Oh, sorry, this and this?
This and above one.
These two have 0 free part. That's right. Yeah. So most of the time, what you'll see is simply a large finite group, and some of the time, what you see is typical picture is a small free part accompanied by a very large torsion. Still upcoming. Yeah. Any other questions? Okay. All right. So here's what I'll talk about. 305. Okay. So, question. So the first thing I want to talk about is I'll describe 2 heuristics. So this is kind of a plan. Heuristics as to why this should be true. Okay, so when I say this, I mean this kind of exponential. This means exponential growth of exponential growth of this. Okay, so I'll describe 2 heuristics for it, and they're quite different, and so they both have some advantages and some problems. But so I guess probably this will already take up the rest of the time today. The second thing I'll talk about is analytic torsion. All right, so let me just tell you roughly now what that's going to be. The statement I make here, I'll say it in the context we've discussed, but it's literally true only in the co-compact version of it. So this. So let me say that the following, the statement I'm about to make is really due to work of Ray, Singer, Cheeger, and Mueller. So this comes from a statement that has no number theoretic, is not of number theoretic nature, but here it is. It says that the size of this group, okay, multiplied by a number r, so I'll call this a regulator, is equal to, well, there are different ways of saying it. For now, I mean, I'll state it exactly when we get to it. For now, let me just say you can think of it as a value of the Selberg zeta function. Okay, I don't really like thinking about it in this way, so I'll say something different later. But this is, again, in a way that I'll make precise, this is a sort of non-abelian class number formula. So this is a, and again, I have something more precise in mind when I say that, so class number formula. Okay, anyway, what this R measures the size, so R is 1 if this is really a finite group. So it measures, in some sense, it is finite. So R measures the size of the free part. So R measures the size of the free part. There are several ways you could think of measuring the size of the free part, that they're all equivalent up to constants, but so I think this is a good way to think of it, and I'll explain more about why later. But one should think of this object, it measures, it's kind of a non-abelian class number. Okay, and again, there's something precise to be said. So you should, in some way, it has certain features which are like usual class numbers, and in particular, it has this sort of analog of a class number formula. The third thing I want to talk about is I'll talk about this regulator R. Okay, this regulator R is itself extremely interesting. Okay, I think for a long time I somehow ignored it because I was focused too much on this, but it is something very interesting in its own right, and I'll talk in particular about its relation with L values and with heights of elliptic curves. Let me just say L values and heights. Okay, so that's all right. So that's the plan of the lectures, and for the rest of today, I want to talk about heuristics as to why, why we might expect this kind of phenomenon. Okay. So. All right, so I'm going to say two different heuristics as to why you expect this thing to behave this way. So let's say first, okay, so first heuristic. So I'll say the heuristic, which is pretty simple-minded, and then I'll discuss then I'll discuss it for a little while, including some ways in which it's not right. So we can give so I haven't yet described how when we come to this analytic torsion story, by the way, when I say I'm going to discuss this, like I think the main point I'll get to, I'm not going to. Or maybe I should say. Yeah, when I talk about 2, I will say some 2 and 3. I will talk about some, like we have several theorems in the direction of this, which I will discuss when we later on. But I'm not going to go into the proofs of anything. I'm just going to try to give some sense of the story. All right. So the first heuristic is, so we can write down a presentation. For if you gamma naught n, so from now on, when I write gamma naught n, we're always dealing with gamma naught n inside. So here, this is inside SL2 of O, where O is now an imaginary quadratic order. All right, so always from now on, I never mean inside SL2Z anymore, always inside the imaginary quadratic thing. So we can write down a presentation for it using the geometry of a fundamental domain. of the fundamental domain. So in other words, so this gamma naught, this guy now acts on hyperbolic 3 space, and I will say more about that. And using the geometry of the quotient, you can write down a presentation for it. Okay, so I won't go into that, but what does this presentation looks like? So this gives a presentation of the following type. So it gives you a presentation with some generators, x1 up to xg. Okay, and these generators have to do with, you take the fundamental domain and you look at fundamental domains adjacent to it. And then you impose some relations. Okay, and if you do this, there's more than one way to do this, but if you do this carefully, you see you can get the same number of relations as generators. Okay, so this number, this group, it has a presentation, some generate the same number of relations, and G is some measure of the size of the fundamental domain. Okay. Now, to get the size of this fundamental domain is going to be essentially, it's a measure of how small this group is. So it's more or less proportional to the index of this group gamma naught n inside gamma naught 1. And so very roughly, that's going to be of the scale n squared. Okay, I'm talking this approximate sign. It means really approximate. Okay, it doesn't mean like n squared log n. It's all the same.
I'm sorry, when you say we can do this, you mean we can do this fairly explicitly, right?
Yeah, I mean, if we did it because this is, firstly, there's some issues because it's non-compact, and that naturally gives you fewer relations. But yes, we can do this explicitly. Sorry? Yeah, if you have something written as an explicit complex, you can always write down a presentation for it. Which is not to say it's easy to algorithmically write a program to do it, but it's in principle it is not. It is no issue. Okay, so now I'll say something more about the nature of these relations in a second, but okay, so it's still there. So if we abelianize this guy, what we get then is we get g copies of z. So this is just like the computation that I said at the start. If you have a group with an explicit presentation, to make it abelian, you just have one copy of z for each generator, and then you quotient by some vectors, which I'll call v1. So the subgroup generated by some vectors, v1 up to vg, where vi is, if you look at this example, it's kind of the exponent vector of this relation Ri. Okay, so for example, if Ri were something like what do I call them? x2, x5 inverse x2, x3, then the corresponding vector vi would be let's see, 0 in the 1, 0, 2, 1, 0, minus 1, and then 0. Okay, so these numbers here, the 2 means that x2 shows up twice. It doesn't matter where, the order doesn't matter. Minus 1 is x5 shows up with exponent minus 1, and so on. So, okay, now, given that this presentation came from geometry, okay, so these relations come from something like edges of the fundamental domain. Okay, the generators come from something like faces, the relations come from edges, and you can see these VIs most of the entries of the VIs of VI will be in either -1, 0, or 1. Okay, so that's not, it's something about how we can explicitly construct the presentation. Okay, so now we have to address the problem of how to bring down that board. And let's see. Right, so let's for a moment forget about our exact setting, and we can consider the following problem. So if we choose, let's say, random vi in z to the g with entries you just choose all the entries at random, we can, so that's some sort of naive model of this, we can ask how large this group is going to be. Okay. And the size of this, okay, so you take zg and you take the quotient by the group generated by these vectors. The size of this is going to be the determinant of the matrix you get whose rows are given by these vectors. Okay, the absolute value of that determinant. And if you take a matrix, right, and you just start filling the entries in with, say, zeros, ones, and minus ones at random, the size of the determinant you expect, so depending on how exactly you model it, you expect this to be of size exponential in g, maybe g factorial. So I'll just say one expects this, randomly speaking, to be exponential in g. Okay, and you could just, if you want, you could just model this yourself. You'll see immediately that it's at least of the scale e to the g or e to the g log g. So this very naive thing is at least so remember I said this quantity g is of size roughly n squared. So this is at least, I mean, such a heuristic is certainly not, makes no precise conjecture of this nature, but at least it suggests to you that, so in other words, you can in some way make a random model for this group gamma naught n from a geometric point of view. And if you just think about that geometric model, it does suggest that the abelianization should be large. Okay? This model, so if this is, as a first heuristic, this is not bad. There are several problematic things about it. I'll discuss a couple of them, but it sort of gives you the right idea of what's going on already. Are there any questions? Yeah.
Can you say where this model breaks down for SL2Z, for subgroups of it?
Well, SL2Z doesn't have such a, SL2Z and subgroups are basically free groups, right? So I didn't say, I mean, specifically I didn't say where this fact the presentation is balanced came from. But for SL2Z, and their subgroups are up to small phenomena, they're free groups. So there are no relations at all. Yeah. This is, another thing about this heuristic is that it's not very robust. Like if you're analyzing SL3, it's much harder to figure out from this naive point of view what happens. Yeah.
Can you make a conjecture from the value of the Hilbert zeta function? About the size of this gamma naught?
Yes, and I did. That's the conjecture which is there. So this number comes from thinking about this.
No, but I was wondering, can you just use somehow make a conjecture about the central value and then transfer that to the conjecture of gamma naught n?
That's essentially where this comes from. Yeah. 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 And the problem in this story is not the analysis of the Hilbert zeta function. Okay, or I have to say exactly what that is, but that's not the issue. The issue, well, there are two issues, but the most interesting one has to do with this R.
Can you say why most of you?
Is the heuristic scaled by the free part?
Sorry?
Is the heuristic scaled by the free part? Is there a free part?
So, okay, I'll talk about that right now, how the free part affects the heuristic. There's another question?
Can you give an idea of why most of the entries should be -1, 0, and 1?
Yeah, you see, this comes from the geometry. There are different ways to construct it geometrically, but these relations look something like this. You have a bunch of fundamental domains that meet around an edge, and then the relation is a product of elements is equal to 1. So as long as not too many things meet at an edge. Okay, so no, I forgot what I was going to say. Oh yeah, okay. So yeah, we'll talk now. Yeah, in this whole story, the most interesting thing is what happens when there's a free part as well as a. So okay, so this is a statement of this heuristic. Now let me say remarks. Let me call this heuristic, heuristic A, okay, because there'll also be a heuristic B. So remarks on heuristic A. I guess I'll probably only have time to make one of these. So there are 2 comments I want to make about it. So first, what happens if, so what does this say about the case where gamma naught and ab is infinite? Sorry? It has probability 0, but nonetheless it happens. It certainly it certainly has probability that's exponentially small in G. For one thing, that's already a point, is that it happens much more frequently than this. Okay, so it has, if I just vary this number n, it happens far more than you would expect from literally this. Okay. Right. But then, so let's look at a case. So if suppose this group were actually infinite. We're infinite. Then this matrix, this happens when this matrix is, whose entries are these VIs. This happens when this is singular, okay, has rank at most, well, it has rank less than G. So let's suppose, just for the sake of discussion now, that it has rank G minus 1. Let's say its rank is G minus 1. So firstly, where's the equality? Certainly this, so there's a modification of, so let's say a modified version of star. What did I call A? Okay. So the following modified version of star still holds. Okay, in what I'm about to write, let me assume that A is symmetric. Okay, just because there is a reason why this is a sensible thing to assume, but it's not. Mainly, it just makes the formula a little bit simpler. So what you still have is the size of the torsion part of this group. Okay, so now we just take the finite part, and now we multiply it by something, which I'll call R because it's going to be similar to the regulator that will occur later. And this is, I'll call it det prime of A. And this det prime of A is the product of the non-zero eigenvalues. Okay, so there's still the determinant is 0, but one still has something like this, and you still expect the product of non-zero eigenvalues to be pretty large. Okay, one expects this still to be of exponential size. I have to say what R is. So here, this R is given by, I'll write, so it's given by the sum of xi squared, where x1 up to xg is a generator is an integral generator. So let me say a primitive, meaning all the coordinates are relatively prime, primitive integral generator for the kernel of A acting on z to the g. Okay, it has rank, it's an integer matrix, it has rank g minus 1, so it has a kernel. And so you can pick a generator for that kernel. And this R measures the size of that generator. Okay, so another way to think of this, so another way to think of R is that it measures the size, it measures the size of a homomorphism from this group to the integer, from a homomorphism from z to the g quotient by this v1 up to vg. So this is no longer a finite group, so it has a homomorphism to z, and explicitly, this homomorphism sends let's say it sends the m1 up to mg is sent to sum of mi xi, I equals 1 to g. So this sum of xi squared kind of measures the size. If you actually try to write down in explicit coordinates a homomorphism to z, the R measures how large that is. So now you have this problem, which is why should, so for gamma naught n ab, for this to be large, R should be small. Okay. So let me say this. Yeah, this naive thing above will have a precise. You can think of it as a kind of crude version of this analytic torsion formula, which is literally right. But anyway, the fact remains is you have a competition between two things. One is the size of the finite part of this group, and one is this R. Okay? And this, for example, this happens in the context of class groups. If you take the class group of a imaginary quadratic field, the size of the class group times the size of the regulator is something you can compute explicitly with L functions. But what happens is in the real quadratic case, the R always wins. Almost for typical real quadratic field, the regulator is very large and the class group is very small. Okay? So this does not happen in this setting. Okay? So for some, at least from an experimental point of view, most of the time that you see it, the R does not appear to be that large. And so this was something, I mean, trying to understand this was one of my, something that motivated me for a long time, understanding why it should always split up, so to speak, in favor of this, the finite group part. OK, so I think I'll stop there. And next time I'll start off. There's a second remark I have on this heuristic where I'll explain a way in which it's definitely wrong. Just to like this heuristic is clearly crude, and I'll point to at least one way that it gives you wrong answers. So, thanks.
Are there further questions or comments?
So what's the heuristic part in the two signs? Yeah? Can you prove that the size of the fundamental domain is related to G? Or?
Oh, sorry, you're saying what part of this is heuristic? Yeah, the part of this is heuristic is that you have you have no actual idea this determinant is as large. So you really could write down a presentation of this rough size, but that determinant might be 1 for all you know. Yeah.
Yeah.
Is there, say, any connection to, say, like the class group of binary quadratic forms?
No, so at the start of next time, I'll in particular explain what I mean by non-abelian class formula. Yeah, so there is a connection. So next time we'll talk about more what this has to do with algebraic number theory. I'm sorry? The number of cusps is the class number, but this measures something else.
The fact that you're playing the sum of squares here, it's again under the assumption that you have your random generator.
No, I think this is an okay. So I might have misremembered this, but I think this is more or less this is an exact equality. Just a fact about quotients of.
So wouldn't you expect a volume instead?
This is you can think of it as the volume of the kernel, if you want. Yeah, because or the square of a volume. It was this confusion about squares that I was.
Square, yeah. By the way, you might explain why you had n squared.
Oh.
In the main formula.
No, Laurent makes a good point. So, sorry, I should have explained this a little bit more. For SL2Z, this index would be essentially of size n. But because it's over an imaginary quadratic field, it's the norm of the ideal generated by n, which is n squared. This is relevant.
Can you generalize this something like for a integer, let's say Eichler order of some division algebra, the same kind of thing?
Yeah, as I said, the conjectures that I'll talk about, the conjectures are completely general. If you look at my paper at Bergeron, they are formulated for any group. Isn't it? Yeah. What is not the methods? Okay, so later on I'll point to things that are more specific. But this conjecture that I wrote, for example, is completely general.
So what is the difference in? So if I understand, non-abelian versus abelian, it's with respect to the class number formula for imaginary quadratic field, which is torus is abelian. Is there non-abelianity related to the class number formula, so the computation of Tamagawa numbers?
No, I'll explain exactly what I mean. It has a precise meaning, which is not, but I'll say it next time.
And so you told me, so the L value is at 1 here.
Oh, the Selberg?
No, it's 0.3 and 1.3.
The L value is at the center.
At 1/2, so it could vanish.
So when I say that no, this is something like more like it's up to a rational number in L value, which the rational number can be 0, but maybe it's better to, it's a height, or so it seems.
You guys, no more questions.
So I'll just remind you quickly at what point we were yesterday. So last time, the thing we discussed was that, okay, so O is an order in an imaginary quadratic field, so something like this, where B is less than 0. And so N is an element of this. And we define the congruent subgroup, A, B, C, D, where so these now belong to O. The determinant is 1, and N divides C. And so the phenomenon which we want to discuss is that when we take this group and abelianize it, so this the the size of this, or the size of its torsion part, if it's not finite, grows exponentially. So this was with n squared. Okay, so I gave yesterday a more precise conjecture, and we'll revisit it later today. But that was the kind of phenomenon that we were discussing. And okay, so the plan of the lectures are is that so. Okay. So I'm still in this. So after I set this up, I described a heuristic, which at least very crudely explains why this should be large. And so I'm going to spend more time talking about that. I'm going to finish discussing that heuristic from yesterday, and then we'll talk about another heuristic. And probably by the end of the day, we'll start on this analytic torsion. So this first heuristic from yesterday, so what I called heuristic A from yesterday suggested that when you take this group and make it abelian, you should model this as, so can be modeled as integers where for v1, vg, these are let's say random vectors with some all right, so with entries, let's say -1, 0, 1. Okay, so this came from looking at how a presentation for this group coming from geometry might look like. All right, and here G should be very roughly on the order of n squared. Okay, so this is what we discussed yesterday. Now, I want to make a second. I want to explain one way in which this heuristic is definitely inadequate. So, okay. So this heuristic, as I said, it's a crude heuristic. It very roughly, correctly predicts the size of this. But if you ask about anything finer, it's really wrong. So let's examine what this says about. So far I just discussed its size. Let's look at its actual group structure. What this suggests about the group structure. Okay, so if we're going to talk about in other words, is it a cyclic group or a product of cyclic groups or so on? And I'll explain that this heuristic really gives you a wrong picture if you ask such a fine question. So there's something essentially missing with this, and it's sort of important to be aware of that. Okay, so if we're going to talk about the group structure, we might as well look at it prime by prime. Okay, so if you believe this heuristic, let's just look at a single prime p, and I'll look at the p part. Okay, so in other words, I throw away everything. I throw away all the torsion that's prime to p. Okay, so I just keep whatever factors of z mod p squared, and so on. So if you believe this, you would think, I'll write this, meaning this can be modeled as, you take now p-adic integers to the g, quotiented by. So if you believe this, it's reasonable to believe that, let's just sort of take p parts everywhere, where these v1 up to vg, you choose them random. You choose random vectors in Cp to the g. Up here, there was some 0, -1, 1 entry, but you don't expect that should have any influence on the group structure. Okay, it's a kind of an Archimedean constraint, not a. Okay, so if you believe this, you think maybe this is a reasonable model for how the p part of this behaves. You take some fairly large number g, you take zp to the g, and you quotient it by this. Now, this. All right, so this is some way to produce a p group, and in fact, this way has already shown up yesterday in a different context. So in fact, you can very precisely understand what this process produces. Okay, so if you take quotienting zp to the g by g random elements, vg, at least in the limit as g goes to infinity, it produces exactly the same distribution that you see in the Cohen-Lenstra heuristics. So I'll say this precisely. Produces the Cohen-Lenstra distribution. Okay, so by this I mean that if G is a finite abelian P group, then, okay, let's look at the probability. The probability that, all right, so take some integer G, pick, so to speak, a G by G matrix of p-adic numbers at random and do this quotienting by the rows of that matrix. The probability that you get G will be exactly the probability that we see in Cohen-Lenstra, which is the product from 1 to infinity, 1 minus 1 over p to the I, divided by the number of automorphisms of G. All right, let me say it's not maybe so relevant for our story, but in a second I'll say why you expect to see this exactly the same thing in the Cohen-Lenstra context. Okay, that's a separate but interesting story. But what I do want to say is that in particular, just as Fouvry discussed in his lectures, the probability of getting a group like Z mod P to the K is very small. Okay, so Fouvry discussed Z mod 3 times Z mod 3. If you do Z mod 3 to the K, this probability will be on the scale of P to the minus K squared. Okay. And if you look at data, if you go look at a table of data of this, a bunch of different n, you look at the abelianization, you see that this is not realistic. Okay, you see many factors of Z mod P much more often than you would expect. Okay, so this doesn't match the data. Okay, so I'll say this is, I think there's a clear guess as to what is missing from this heuristic. But let me just have a small aside about why this same thing shows up in the Cohen-Lenstra context. Are there any questions up to here? Yeah.
So you choose a problem with
yeah.
entries minus 1 to 1?
Okay, so for the ease of analysis, let's say we choose them at random with respect to the Haar measure. Okay. However, in practice, I know there are theorems of this sort, but I kind of don't know what the state of the art is. But in practice, if you simulate this, you find pretty much any way you pick them, you will get the same distribution. Okay, that is minus 1. Any reasonable distribution, it seems it's very insensitive to how you pick them experimentally. But when I make a statement like this, let's say that I mean that VI are chosen uniformly with respect to Haar measure. Any other questions? Okay, so this is a slight aside, but I thought it was worth making because we're also talking about the Cohen-Lenstra heuristics in another course. So why should this show up? Why does this show up when you model when studying class groups? Oh, one thing I wanted to say is this equality here. Oh, oops, someone should have said, sorry, limit as g goes to infinity. Okay. Okay. The convergence here is extremely fast. Okay, so as long as g is slightly more than the number of generators for g, this would already be very close. And the proof of this is an elementary exercise in algebra. Okay, it's not much harder than knowing the number of invertible matrices over Fp. Okay, so why should this same distribution, which I've said is not correct in this case, but why does it show up in starting class groups? The point is that you can also, if you take K as an imaginary quadratic field, okay, so the class group of K is by definition the group of all ideals quotiented by the group of principal ideals. Okay. Now, this is the quotient of two infinite groups. Okay. So, but you can replace this by something that's kind of finite and easier to analyze as follows. So let's say let S be a large set of prime ideals. So for example, maybe you take all the ideals with norm, e.g. all with norm less than some very large number. This should depend on K, so some big number. And so if S is large enough, you can replace this by kind of finite version, where we just look at those ideals, the ideal generated by primes in S. Okay, so you look only at those ideals who have all their factors in S, and you quotient only by the principal ideals intersect this set. Okay, so principal intersect the same set. Okay, now this top thing here, so it's what you can get from all the primes in S. It's clearly a free abelian group of rank equal to the size of S. Okay. The bottom thing, it comes from all elements of K. Principal ideals are just things generated by K, but they should have all their factors in S. Okay, so this, in other words, comes from, okay, sorry about that. This comes from the S units, okay, the elements of K, all of whose prime factors lie only in S. And Dirichlet's unit theorem shows you this is also a free group of rank S. Okay, that's where the imaginary quadratic is used. If it were a real quadratic, it would be S plus 1 at this point, and that you would get it. So the point is the class group of an imaginary quadratic field is naturally presented as a quotient, in other words, of some free abelian group modulo the same number of relations. Okay? So in some sense, so that kind of explains heuristically why you should expect this distribution. Okay? There would need to be some conspiracy among these relations for it not to happen. So this model of group shows up. I'm not saying it also shows up in other contexts. It's a very natural model that you take a large number of generators and quotient by the same number of relations. Okay, now, what was I going to say? I was going to say, yes, what has gone wrong here? Are there any questions? So, I think the short thing which has gone wrong is that this. So let me say it this way. I'm going to say something. So suppose we looked not at this, but we looked at a gamma that was a group that was not arithmetic. Okay, so you take you take something like a hyperbolic 3 manifold, which is not arithmetic, and you take its fundamental group, and you go through the same story. Well, in fact, Nathan Dunfield and Thurston showed that at least under a certain model of random such groups, you really do get this Cohen-Lenstra distribution. Okay, so the fact this doesn't seem to hold is related to the arithmeticity of, so it's somehow related to So this is related to the failure of the model to account for arithmetic symmetries, which, and by that I mean the Hecke operators. Okay, this model knows nothing about the Hecke operators, and the Hecke operators greatly change the. All right, so let me just finish. There's a very similar phenomena to this failure, so I'll just comment on that, and then we'll be done with this heuristic. Okay, but so in other words, yeah, this heuristic, this is the main point. This heuristic doesn't account for the Hecke operators. This is one way in which it becomes visible. It gets the group structure wrong. Right. So what we did here is I took a random G by G p-adic matrix and I formed a group out of it, and that's its distribution. And the story, it has some parallels. This has some parallels with the kind of classical random matrix theory. Okay, so just to give you an example of such a parallel, here I wrote so this probability of that you get z mod p to the k. Okay, I said it's very small. Why is it so small? It's because this G by G matrix is most unlikely. It doesn't want to have many eigenvalues near 0. Okay, so this is actually exactly the same phenomena that if you take, I think if I did compute right in the GUE matrix ensemble, so random Hermitian matrices, the probability that you have k eigenvalues in a window of scaled length epsilon has exactly the same behavior. Okay, it's epsilon to the k squared. So there's this sort of Cohen-Lenstra story has some reflection of what you see in random matrix theory. It's much easier than random matrix theory. Okay, but you see some parallels, and in particular, this failure. There's a parallel failure to do with random matrix theory. So the failure of this naive model to, well, okay, above. So it's kind of similar to an analytic failure, which is that to the failure of, say, of random matrix theory to model the eigenvalues of. Okay, so if you don't know what I'm talking about here, it's not going to matter. But I'll just say this: to model the eigenvalues of gamma mod the upper half plane if gamma is arithmetic. So something physicists noticed about 20 years ago is that typically if you take a quotient of the upper half plane and you take its Laplacian eigenvalue, the gap statistics look like random matrices, but they don't if it's arithmetic. Okay, and that's sort of presumably because the presence of Hecke operators forces it to behave in a non-generic way. And so this failure is kind of parallel to that one. Okay, this where there's some similarities to this. Okay, so I think that's the end of the first heuristic, and now I want to. So now I want to talk about the second heuristic, which is much more specialized, but it also gives me a chance to talk about some of the reasons one might be interested in this story in the first place. Are there any questions? All right, so for heuristic B, I have to describe a little bit the relation of this to the Langland story. So So let me start by saying one. Let me start by briefly saying something which happens in the classical case over Q, and then I'll describe the parallel phenomena in this setting and why it's in a way more interesting. So over Q, right? So if we have F, which is a weight 2, so F is a weight 2 holomorphic form of level n. With rational coefficients and a Hecke eigenform, and so let's say okay, so it looks like some AN to the QN. So Eichler and Shimura made this wonderful discovery that they could associate to F an elliptic curve. So this is due to Eichler and Shimura. E, let's call it E sub F, which is an elliptic curve. And it has this amazing property that this AP here is related to the number of points on this over FP. Okay, so number of points of this over FP. So this is due to Eichler and Shimura. Okay, so that's just P plus 1 minus AP. And in fact, you don't, there's a way you can just kind of, if you don't even have to remember the full elliptic curve, one can just remember the Galois representation on the Tate module. Okay, so if you don't know what that is, don't worry about it. So Galois representation. So I'm just saying this so that if you've seen it, it'll make contact with what I'm about to next, but it doesn't matter if you have not seen it. And this has the some property, trace of rho, that its traces on Frobenius elements are related to these APs. Okay, so that's the story over Q. Now let me now say the corresponding story over our imaginary quadratic. Okay, so over our ring of integers in an imaginary quadratic field. Now, yeah, maybe I should just remind you that, as I said at the start of yesterday, if we didn't know about the space of weight 2 forms, we could nonetheless extract all the information in it from just abelianizing this group. Okay, so as far as the Hecke operators go, they have exactly the same information. So over O, all right, so I'm going to, for example, here there's also a statement if the coefficients are not rational, but I just stuck to this because it's simple. So again, here, let me make the simplest statement I can, and then I'll say something to try to make it a little more palatable, and then I'll talk about so it's involves the work of many people. So let me start. So the simplest, I'm restricting to a simple case to make this simple, so let's suppose that we are in a setting where the P part of this, okay, so gamma naught n here, right? We're in this, now I'm over this imaginary quadratic field. Let's suppose that the P part of this just consists of a single factor of Z mod PZ. Okay, it's not important, but it just makes the statement as clean as I can make it. All right, and then in this setting, all right, so let me pick an element, a non-zero element here, which I'll call alpha. So here, you can make a representation, so it goes from the Galois group of, so K is going to be the corresponding quadratic field. So it goes from the Galois group of K bar over K to GL2 FP. Let me GL2 Z mod P. So it's the same Okay, same P here and here. So I'll write it, and then I'll sort of, in a special case, I'll try to make it a little more friendly. So, and it has the following properties. It has many properties. I'm not listing all of them, but two important ones are it is unramified outside n times p, and for any prime q, the way the qth Hecke operator acts on this alpha is by multiplication by trace of the Frobenius at q. Okay, if you've never seen this kind of thing, this looks like sort of incomprehensible. So let me just pick a special case and try to make this a little more friendly. And so, by the way, this is a lot harder. Okay, I'm going to talk about the history of this in a second. But this is a lot. This is not due to This is much harder. So let's just to illustrate the kind of what this means. Let's take the case when P is. Yeah, it should be rho. Yeah, let's call it rho. Let's just call it rho. Okay. In this setting, I just have this one. Yeah, thank you.
P is prime to n?
P is prime to n. I don't think it matters, but maybe this there's only one n. But I don't think it matters that P is prime to n. Oh, wait, what did you say is prime to n? Oh, yeah. OK, but maybe Q should be prime to n. Yeah. OK, so let's just take the example when P is 2. OK, so I just want to spend some time saying that this, how should one think about this? OK, because so when P is 2, I mean, in practice, so let's say P is 2. So you do Abelianize this, and you see that the 2 part is just a Z mod 2. In practice, if you actually do this, you'll have this annoyance. This won't be surjective a lot of the time. But let's say it is surjective. So say that rho is surjective. So what I'm going to try to do is translate this right-hand side into something more down to earth. So rho goes from the Galois group of k bar over k. It goes to GL2 Z mod 2Z. And this is a group with 6 elements. It's isomorphic to the symmetric group on 3 letters. OK, so to give this map, to give the map from the Galois group to S3 is exactly the same as giving a cubic field. OK, so rho determines. So to give rho is equivalent to giving a cubic field, which is not Galois. OK, so a cubic extension. And yeah, if it's not Galois, you'll get a S3 extension from it. And now I'll translate these other 2 properties, A and B. Okay, so A says that this L, the discriminant of L, is divisible only by primes Q dividing n times p. And condition B says, if you just go through the translation, what it says is that if you, OK, so I have this, here's this alpha. One thing I've sort of said here without explaining is that there really is a way that the Hecke operators act on this. Okay, so I said this at the very start when we were discussing weight 2 forms. I said the Hecke operators act here, and they compatibly act here. Okay, so if you sort of think through this and figure out how to translate the Hecke action here to here, then exactly the same thing works over here. Okay, but I never actually wrote down the definition. But whenever you do this, take an arithmetic group and abelianize it, the Hecke operators act on it.
So the alpha is an eigenform, this is automatic?
It's automatic in this case because I assume that the p part is just Z mod p. Yeah. So, right, and this other assertion says that, what does B say? It says TQ of alpha is non-zero if and only if Q, so Q is a prime of K, is inert in L. Okay, so when you, so something that at least at some point I did to try to make myself feel better about this is for small p, you can translate these assertions to things about explicit number fields and the way that primes split in them, and then you can go and test it numerically, and it's very satisfying to see you can. So as you see, for small p, this is really these statements. The content of the statement is something very explicit. Okay, so I'm going to talk a bit about the history of this. Are there any questions? All right, so this was, so on the one hand, in some way you expect it perhaps by analogy with this. But there's something, so let me first say, so this has been proven very recently by Peter Schulze. But I want to say some of why it's so much more subtle than this, okay? And some of the history of it. When we look at, in the case over Q, as I said yesterday, this thing is essentially, it's more or less a free group, okay? So I said yesterday it's some many copies of Z plus a small finite group. Okay. Now, the problem you have here is a situation like this. This Z mod PZ is not detected by anything in the classical theory of automorphic forms. Okay, the classical theory of automorphic forms, it has things in objects that exist only in characteristic 0, like Laplacian eigenfunctions and holomorphic forms. And so it has no hope of seeing this. And actually, so the reason I got interested in this problem in the first place is somehow all the standard techniques of automorphic. So this alpha, it behaves just like a modular form. It has every right to be called a modular form, but none of the existing story of the classical techniques apply to it. And in fact, so the idea that you should be looking at these, that one should think about the possibility this has torsion and that you might have this sort of story goes back. So I think it was predicted, and maybe Clausel knows more about the history. I think Avner, Ash, Clausel, and Taylor already knew about this from the 1980s. Is it fair to say?
I think that's how much Sam knew about it, whatever.
Okay, so there's something to be said here. It's not obvious this is something you should be looking at. And it's not obvious that there is this torsion phenomenon here at all. So I think it was an insight to realize this is something worthy of study. Anyway, this goes back to one of the main motivations for studying this with this conjecture I made with Nicolas Bergeron was to show that this kind of phenomenon, this torsion, is actually complete. It's not some sort of strange exception, but it's once you go away from groups like SL2 and Shimura varieties, it's actually the norm. Okay, this is what you see is primarily torsion, and you see very little in characteristic 0. Okay, so all this was just to give you some context. So this story fits in must be a part of the Langlands program. Okay, and still, so now Schulze has proved this analog of the Eichler-Shimura story, but the amount we know about this is still vastly, vastly less than. Okay, so very few of the tools that we know about characteristic 0 modular forms can be applied here. There's also a converse to this assertion, okay, which is not known. So, let me say, I'll just put it in quotes as Sayre's conjecture. Sayre's conjecture is usually understood as a statement about Q, where it's the rational, where it's proven. But so this is should be, so it's a conjectural converse. Okay, and I've said this in the kind of a very simple case where this is Z mod P. But even if this is Z mod P squared, but whatever this is, there is some precise statement you can make whereby you can exactly predict this in terms of Galois theory. Okay. All right, so that's a very short description of how this relates to the Langlands program, and now I will come back to the question of its size. Are there any questions?
I mean, if you have 3 parts on your group, the Galois representation in principle can come from some characteristic 0 more or 4, or you always predict it should come from torsion.
No, okay. So sorry, but when I mean this notation, let's say I literally meant it Z mod P. But suppose, as you said, suppose this lifted to characteristic 0, then correspondingly this would lift to a p-adic and presumably even geometric representation. Yeah. Any other questions? All right. So all right, so now back to the question of size. To the size. All right, so if you have some description of this in terms of Galois theory, you might try to figure out, how large this is by seeing how likely it is that such rho exists. So I'm going to say this this deserves more explanation than I have time for. But so by a non-abelian version of the Cohen-Lenstra heuristics, so I explain why I say this in one moment. The probability that such a rho exists should be roughly 1 over p. Okay, so let me just compare here. Let me say why I'm mentioning Cohen-Lenstra. So the usual Cohen-Lenstra heuristics say that for an imaginary quadratic field K, they say, so for K imaginary quadratic, the probability that P divides the size of the class group is this number, which is 1 minus that number up there. So 1 minus the product from 1 to infinity, 1 minus 1 over p to the I. And sorry? Yeah, I think this is a I apply the statement above to g equals 1 and then take the. So this is, all right, now this is roughly 1 over p to first order. Okay, but we can reinterpret this in the following way. Okay, this is the same as the probability that there's a non-trivial homomorphism from the class group to Z mod PZ. Okay, and by class field theory, this is the same as there being an unramified homomorphism from the Galois group. Okay, so this way you can think about the Cohen-Lenstra heuristics as telling you, measuring something about how likely is it that you have a abelian extension of a number field, and in this context the answer is supposedly 1 over p. So when I say a non-abelian version of these heuristics, what I mean is something that describes for you the chance of you having homomorphism in the Galois group to some non-abelian group. Okay, and this exists, I would say, so largely due to work of Bhargava. So let's say Bhargava formulated this for the symmetric group. And then if you take what he did and then you apply it very recklessly, you come to this claim. Okay, so suppose you believe this for a moment.
Is it the same as what Torsion and question did for columns with no
Yes, in some I think yes in some idealized situation when there's no Archimedean story. The Archimedean story is very problematic because some elements are forced to be of order 2, and so if there were no Archimedean places, it would be like that. Yeah, but sorry, maybe I should say that. So another way, how would you guess what these heuristics are is related to what Emmanuel said. If you didn't know them, one way you can do it is you can think about a function field case, and there is sort of a clear guess of what the answer is. So that's how you might discover this if you didn't know it. Okay, where are we? So if you accept this, and I admit we're somehow deep in the realm of heuristics here, but if one accepts this, that says that the size, so how big is this group going to be? Well, it's going to be at least for every p, every prime occurs with the probability of 1 over p. And this is infinity. So you might think it's problematic that this heuristic predicts infinity for an integer. But I think, so if you were to, you could apply the Cohen-Lenstra heuristics the same way to predict, try to guess. If you just went prime by prime and applied the Cohen-Lenstra heuristics to guess the size of a class group, it would predict that imaginary fields have infinite class group and real fields have finite class group. Okay, so you should take this with a pinch of salt, but at least this suggests that it should be large. Okay, one advantage of this type of heuristic is it works very well when you replace, when you go to a general setting. That is, you replace SL2 by a bigger group, or you replace your imaginary quadratic field by another field. This always gives an answer, and that answer seems, as far as people have been able to test it, to really be, experimentally, seems so far to be right. Okay, I'm not going to talk about that, but that's the main virtue of this heuristic, is that it is very, it's much more generally applicable than the previous one. Okay, so that's, I think, the end of heuristics, and now I'm going to talk, we will talk about next about analytic torsion. And to start that, I'm just going to talk about, I'll introduce just hyperbolic 3-space. So I'll just be making, I think, definitions for today so that we can look at the formula next time. Are there any questions? Yeah.
So gamma naught n, abelianized gamma naught n is big. That means it has to have a prepart? Or?
No, well, it's unclear. You know, it's somewhat open to interpretation. But I interpret it in the way that I want to, which is that the torsion part is getting very large. Yeah, so it's, yeah. Like, for example, if you literally apply this heuristic, it predicts that the probability that modular forms exist is 0. So there, you have to be a little bit careful about the realms where you apply it. But anyway, I'm not saying so. I found this to be quite reliable as long as you're a bit cautious about how you use it. All right. So now, so now we're going to talk about analytic torsion. But well, maybe I write the formula now, and then our job will be to define the quantities that are in it. Okay. So this formula, well, again, let me attribute it after I write it. So what I'm about to say is true. So true if, oh dear. Okay, it would be true if this quotient were compact, and if not, it's much more delicate story. So I'll write a formula which is literally true in this case. The size of gamma naught n torsion part abelianized times r. This is this regulator, which will be the thing which I now feel is kind of the most interesting part of the story. this is equal, now divided by the volume hyperbolic volume. So I'm sorry, I'm going to talk about this hyperbolic space and we'll define the quantities one by one, is equal to determinant of, so over here, there'll be two, okay, these delta naught and delta 1 will be Laplacian operators, and I'll define them. Laplacians on gamma naught n mod h3. This is the Laplacian on functions, that is usual mass forms. This is the function on one forms, so mass forms with some weight. And we need to discuss how you take the determinant of such a thing. All right, this is really, it's a remarkable formula because it says that this object, which is something of discrete group theory, you can compute in an analytical way. And so it was conjectured by Ray and Singer. And I think, so in particular, when Ray and Singer conjectured this, in particular, they defined this in the first place. Okay, so as far as I understand it, the definition of this, how to take a determinant of something infinite dimensional was due to them. So I think it's tremendously insightful that they guessed such a formula could exist. I'll say something next time about how you might guess that, but it's an incredible thing just to guess it's there. And it was proved maybe by Cheeger and Mueller independently. And also I'll say a couple of words. But this formula has nothing to do with number theory. So a version of this is true for any, a version is true with gamma naught n mod h3 replaced by any compact Riemannian manifold. Okay. So I said yesterday, another way you can think of this right-hand side is as a special value of a Selberg zeta function. Okay, so I'll also say more a little bit about that next time if there's time. Okay, but for now, I want to define all the quantities here. This one we've seen. Let me define hyperbolic 3 space in the volume. Oh, and one thing to say is that this R has to be defined too, but for now just say R is 1 if R is 1 if this abelianization were actually finite. Okay, so this R is, is some measure of the size of the free part, so it's a regulator. All right, so maybe just a few minutes on the hyperbolic space, then we'll. Are there any questions about that? All right, so just like, so I've already written it up here. So just as SL2R, so okay, hyperbolic 3 space. All right, so when you study SL2Z, a basic fact is it and even the bigger group SL2R act on the hyperbolic plane, okay, which I'll write as H2 for the moment. So in other words, that's all, as a space, is just a positive half of the complex plane. But what's useful about it, well, one of the things which is important about it, this is that it has a metric that's invariant. So a Riemannian metric where, and that's invariant by SL2R. And then when, the thing, so to some extent we try to study a group like this through the geometry of this. So the analog in this case up here is that SL, for example, SL2 of O is my Z of square root D. This sits inside SL2C, and this acts on sort of an analogous story 1 dimension higher. Okay, so I'll just say the bare outline of it. It acts on a 3-dimensional analog of this space. And in fact, everything is very similar, just 1 dimension up. So this space is now, you can think of it as 3 coordinates, x1, x2, y, where y is positive. The metric is exactly the same formula. The action is by fractional linear transformations. Here, you can see it as being by fractional linear transformations when you think of these in some quaternionic way. But instead of writing that, I'll just show you how some a few basic classes of things here act. So for example, the element 1. So sometimes I think we can also think of this space. We'll think of it as being. Yeah, so it's sometimes nice to think of this as being inside the complex plane times the positive reals, where the complex coordinates are x1 plus I, x2, and y. Okay, and if you think of it this way, so 1 alpha 0 1 sends x1 plus this thing here translates in the complex plane, x1 plus I, x2 plus alpha, y. And this element here, this dilates both the entries. So it sends x1 plus I, x2, y to t squared, x1 plus I, x2, and then absolute value of t squared, y. Okay, and finally an element like 0, 1, 1, 0 acts by kind of inversion. So anyway, you have this geometry now and one thing which you get even before you do anything fancier is that so just the fact that this acts on this geometry gives you something already. So the volume of, you can form the quotient. Okay, so let me just say in the simplest cases, just like the fundamental domain for SL2Z looks like this, in the small discriminant cases, the fundamental domain for that just looks like a sort of 3-dimensional version where you have like something like that. Okay, that's a typical picture. Fundamental domain for these things are kind of built out of things like that. So, right. So you can now measure this because you have this metric, and just that fact is useful. This gives a kind of an intrinsic measure of the complexity let's write this gamma naught n. Complexity, or if you want size, okay, the fact this gives you some number which in some way measures how large this group is. So in terms of this number, I wrote a conjecture last time. Now let me rewrite it in slightly more generality. So my conjecture with Bergeron, the conjecture of mine and Bergeron states that, and it's naturally phrased this way, is that if you take the logarithm of the size of this torsion, so the scale, last time I scaled by n squared, but the natural thing to scale by is this volume. Then you get, this should go to 1 over 6 pi. Okay, now this is not the way I stated it last time. So to recover the form from last time, so the version from last time, you can use the Humbert, the volume formula, which was proven by Humbert in the 19th century. Okay, and what that says is that the volume of hyperbolic 3 space modulo SL2 of O, where O is the order of discriminant D, is given by absolute value of D to the 3/2 over 4 pi squared times the zeta function of Q squared minus D at 2. Okay, so in the case I had last time, this D was -1. D was +1, and the zeta function of Q of I at 2 is pi squared over 6 times this Dirichlet function. Okay, so this constant which appeared last time, really it comes from the value of a zeta function of this quadratic field. Okay, so it's really a measure of hyperbolic volume, nothing more. Okay, so maybe this is a good point to stop, and next time we will discuss what the other things in this formula mean and a little bit about what we can do with it.
Are there questions?
Is there anything we can compare this to in the SL2Z case?
What's that?
The formula?
Oh yeah, the formula of an S.
Oh, not that one. The Cheeger-Muller.
The right model.
Well, the problem is in even dimension, this tends to is at least if you don't twist it in some way, it's 1 for trivial reasons to do with duality. So it has interest only in the odd dimensional case, at least if it's not twisted in some way.
Okay. You will discuss it next time, so maybe we'll ask next question this time. Another question? Okay, so it's not. Thank you.
What I was going to say, I'm going to explain a little more. I wanted to explain the remaining terms in this analytic torsion formula, and then so far I've discussed what we expect and some heuristics for it, and I'll say I'll discuss a bit what we can prove. I just wanted to make a little remark before that, which was in response to a question that Paul Nelson asked last time, which is that I've been talking about imaginary quadratic fields all the time. There is a kind of parallel phenomena which you can see for just classical modular forms. Okay, so that's the kind of thing we've been discussing. So there's a So the sort of thing we've been doing is you take this group and you take its abelianization, and what you find is it has typically a small free part, but it can have very large torsion part. And there's a similar phenomena for SL2 over for just classical modular forms. But it occurs somewhere which maybe one doesn't think about so much, which is for weight 1 forms. Okay, so if you look at S1 of n, that is the space of weight 1 forms. Now, this space, the weight 1 forms are in some ways the most interesting weight because many things one think of don't work here. As the simplest example is there's no dimension formula. Okay, the dimension is typically very small, and it varies irregularly with n. Okay, we have some understanding of it, but anyway, it's very irregular. But it turns out this has a very similar. You can interpret this as part of the classical space of weight 1 forms. You can interpret as so you can make an integral version, I'll call it S1nz, of this space, so that the classical space is just what happens when you take the free part. Okay? Another way to say it is it's possible for a weight 1 form, it's possible to have a weight 1 form mod p which doesn't lift to characteristic 0. Okay, and except for very relatively trivial instances, that phenomenon doesn't happen in higher weight. In higher weight, once you've worked out what the right notion of a mod 7 holomorphic form is, it always lifts to characteristic 0. Okay, but here this can really fail. And this was but this story is much, I would say, much less. So the first evidence of this was given some mod 2 classes that don't lift were found by Mestre, and then some more were found by Buzzard, but these were still relatively sporadic. And then on the basis of the kind of analogy is what I was saying, I had a PhD student who I asked to compute this integrally for many n, George Schaefer, and he found that in fact this really does behave like this. That is to say, it has a very large, typically it has a very large torsion component. Okay, so sort of the classical space of weight 1 forms is like this small tip of an iceberg, but underneath there's this vast number of n very large primes where you have a mod p weight 1 form that doesn't lift to characteristic 0. This story is less well understood. I don't have. So in principle, this is an analog of everything I'm saying, but Schaefer's data is a little bit. So it will be nice to have a conjecture here that this is growing at some specific exponential rate and so on. There are some mysteries in this data which I don't understand. But anyway, so let me just say for now this is less understood, and it would be worthwhile to develop it. Okay. Yeah. So usually we don't think of weight 1 forms, but somehow as time passes, I sort of see them as the most. They have many kind of boundary behaviors which are very interesting. Okay. Right. So here's what I'm going to say. I'm going to right. So what was our setting actually? So gamma naught n. So now O is this imaginary quadratic order. So something like z squared minus d, and we take this group inside SL2O. Sorry. Are there any questions about this story? Okay. So Kevin Buzzard has a nice paper about it. My student's thesis, Schaefer's thesis, online. It's interesting also from just a computational point of view. It's not trivial even to compute these things. Okay, we go here, and remember we have this subgroup. And again, I'm going to say although I'm stating this setting, many of the results are proved only in the co-compact setting, so they should certainly extend here.
Yes. Question. What do you mean by compute in this context?
Yeah. So for example, I give you like some n, like 500, and I ask you to give me a basis for the space of weight 1 forms over the complex numbers, or mod 7. And even over the complex numbers, it's not a trivial question. Of course, it's clearly computable.
Yeah,
but
it sounds like mass forms.
It's better than mass forms, but it's I mean, to say one word, right? You can embed this space in a higher weight space by multiplication, but then you have to figure out what its image is. That is, it's not clear that when you divide, you don't get a pole. Okay, so back to right. So what is the conjecture we've been discussing is that the size of the abelianization of this, and the correct scaling is the volume, goes to 1 over 6 pi. All right. So let me state again this. All right. So as far as, so I spent quite a while giving you heuristic motivations for that. Now, as far as analysis goes, the main way we have to understand this is this story of analytic torsion, and I'll write the names again. This was sort of discovered by Ray and Singer, and the proofs were given by Cheeger and Mueller. And what they say is, well, we can access, at least in part, this thing analytically. So the size of this, again, right, so this statement is valid in the co-compact case. Okay, if I have time, I'll say some, I mean, we now know a fair amount in this case, although short of an incomplete formula. This multiplied by a regulator divided by the hyperbolic volume is equal to, so some ratio of Laplacian determinants. So as I said, this right-hand side is related to a Selberg zeta function. What I want to do right now, well, we've discussed this acts on hyperbolic space, so you know what this is, you know what this is. I'll tell you what this is, and then I'll spend some time saying what we can prove towards this, and then we'll come back, to the extent there's time left, we'll discuss this right-hand side a bit more. But to say, so this, for example, this delta 0 is just a usual Laplacian operator on functions. The one means on forms or in different weight. And so it has some eigenvalues. So 0. OK, so in the co-compact case, it has no continuous spectrum. And this determinant is some way of making sense of the product of the eigenvalues. OK, so we're going to talk about that just by example after, at the end of the lecture. Because, as I said, there's some, you can also think of this in terms of Selberg zeta function. I actually prefer thinking about it this way, because this way it's sort of clearer what the effect of the eigenvalue spectrum is on it. So that's why I say it this way. OK, what is R? This is what I call the regulator. And what it's meant to measure, so R is 1, as I said earlier, when the abelianization is finite. So in general, what it's meant to measure is it measures the size of, in some way, of the free part. OK? All right. So just as in the case of number fields, there's in general it's some expression with determinants. OK. So to keep life simple, I'll just talk about the case where it has rank 1, so I don't have to write down determinants. So let's say that, suppose that this gamma naught n was actually a copy of the integers plus a finite group. OK, so in general, the story will be similar to what I say, but with determinants. So what R is meant to measure more precisely, so in this setting here, right, you have, so you can make, there is going to be, the way I've set it up, there's a unique up to sign surjective homomorphism like this. Okay, so you can just you can project this onto Z, and that's the only up to sign. It's the only surjection from gamma naught n to Z. And what R is meant to do, it's meant to measure that in some way it measures the size of this homomorphism. All right, so I will give you the precise, I mean, it's a precise definition, but I want to just describe. So this quantity is interesting. So let me describe a couple of different ways that you could try to measure this size. And it'll turn out all these ways are from the analytic point of view, the same. Okay, that is, they're all essentially give you the same order of magnitude. From the algebraic point of view, the specific definition of this is interesting because its exact definition is related to other arithmetically interesting quantities. But analytically, so some ways we could measure the size. Okay, so the most naive way is you could just say, well, this is a homomorphism from this group to Z, and let's look at a bunch of small elements here, and I'll just take the largest value it takes. Okay, so sort of there's a group theory way where you just take, let's say, the largest. All right, so you pick some bound for how big your entries should be. So maybe you go up to, so a reasonable thing to do would be to go up to some power of n. Okay, and you just take the largest. You see how big it gets. Okay. But by the way, because you're multiplying matrices, right? If you kind of, if you made this n to the 20, you don't really expect it to get that much bigger because when you multiply two matrices, the entries kind of multiply. So the matrices get a lot larger without phi getting. Roughly, you expect this to just grow logarithmically. So exactly what you put here is not so important. By the way, what we are concerned about for our applications, all we're concerned about will be does this R grow exponentially with n or not? Okay, so if we're just strictly thinking about this problem, we need to understand it only at a very coarse scale. Okay, there's a topological way of thinking about it. So, all right, so I'll say, again, a fact from topology, which is true exactly as stated only in the compact case, and otherwise you'd have to modify it slightly. But if the space of homomorphisms from this group to the integers is isomorphic to the second homology. So I said I'll try not to talk too much about homology, but this will actually be quite explicit, so I'll explain. So this homomorphism phi, you can represent it by something in the second homology of this manifold. So I'll say what the map is. So suppose that we have S, which is a surface inside this three-dimensional manifold. How do we make, I want to say from it how we get a homomorphism like this. Okay, so I'm just going to make this explicit. So this S, okay, I went overboard here. So what you do is you intersect S. You send S to, so the homomorphism, so send gamma in gamma naught n to the number of intersection points, so of S with the path from W to gamma W. So for any W in H3. Okay, so in other words, gamma, if this path from W to gamma W, it's really a loop here, and you see how many times does it intersect this S, counted with a suitable multiplicity. Okay, now given that, what you can do, so over here, by the way, one reason I'm mentioning this, I know it's a little bit a field of what but is that it's actually very useful in estimating R. Okay, so I'll say something about that if we have time. Right, so the question of measuring the size of this, he translates to the question of measuring size there. But over here, there's a famous norm due to Gromov and Thurston, which is that you can just measure the minimal complexity or the minimal genus of such a surface S. Okay, so you look at all surfaces S that induce this, and you see how, in other words, this, write down the simplest possible surface I can here that induces it, and you measure how complicated that surface is. Okay, now that is not now I'll finally come to the definition which is the most relevant, which is the correct definition for this, which is analytic. I'm sorry, are there any questions so far?
Can you please explain what is this way map for the last one?
Oh, sorry?
For the homomorphism group to homology group?
Yeah, so that like it's sort of clear to write just this way. Okay, so it's a fact, not which that this is an isomorphism, but it's not. Okay, so analysis, and for analysis, let me just first remind you of something that we said at the very start of the lecture series for SL2Z. Okay, so at the very start, something I said is for subgroups of SL2Z, all right, we had this pairing between gamma naught n abelianized and the space of weight 2 forms of level n. Okay, and so how this pairing went was something like if you had some gamma here and an f here, you just send it to the integral of f of z dz from w to gamma w. Okay, so there's a similar pairing here, and I'll just say what it is. And what we're going to do is basically transfer this phi over to something here, and then we can measure its L2 norm. Okay, so I'll write this out, but so that's what we're going to do. Phi is represented by a harmonic differential form, and we can take its L2 norm. So, right. So there's a similar story to this. So I'll use the same notation to be kind of suggestive. So let S2 of n be this. So over here you had weight two holomorphic forms, which you can think of as holomorphic differential forms. In our setting, there's no holomorphic, but we can still say harmonic. So harmonic differential forms on gamma naught n mod h3. So you can think of these as being mass forms of a certain eigenvalue and weight. And then there's an exact. This story goes over word for word. Okay, you can pair these by sending it to integral. So exactly the same, so same formula. Okay, so there's a pairing from this, in both cases, a pairing from this to the complex numbers. All right, now having said that, well, so now what happens is there's a unique omega such that phi of gamma is given by pairing with that unique omega. Okay, so what we've done, in other words, is we've taken this discrete object, which is a homomorphism, and we've kind of spread it out over the manifold to get this representative omega, and we define our regulator to be the L2 inner product. Sorry, this symbol is used in two different ways, but this is the L2 norm on the manifold, so it's like a Peterson norm. Okay. This object is very delicate. I'm going to be saying more about its algebraic properties in the next lecture. It's not so hard to try to see what it is up to rational numbers. Okay, but if you're interested in the size of something, it's not so great if you know it only up to a rational number, and that's very subtle. Okay, so I don't. So next time I'll also try to say, okay. I'll try to mention some problems in the next lecture also. But the point is, I've spent the time saying these three things because they're actually all essentially, from the size point of view, they're all of the same. They're all essentially the same. Okay, that is, so these all have, I'll just say essentially the same size. So the most useful of these is and this is not a hard fact, but maybe it's nice to have all these. The most useful is the relationship between B and C. Okay, and if you want an exact statement, you can see my paper. I'll refer to it again. So I'll say this is my paper with Nicolas Bergeron and Haluk Sengun, and they're okay. It's certainly not a hard fact, but we just write down exactly what I mean when I say that these have. And we don't write the relationship with A, but I don't think it's very hard to check. Unfortunately, A is almost useless for like in somehow in the sense that computationally this phi is easy to compute, but theoretically it's very difficult to get a hand on. Okay, theoretically what's easy to get a hand on is this omega because it comes from automorphic forms or physically constructing a surface, which you could also do by geometry. Okay, all right, so that is what R is, and next time we're going to talk more about R, and it's especially what exact, how is it related to L functions and so forth. So it's very, all right. So now let me. I still have to say something about this, but let's now pause, and I'll tell you sort of what we know how to prove in the direction of this conjecture. Okay, so the only real tool we have to prove things like this is this formula. But even here, there are still many obstructions, which I'm going to discuss. Are there any questions?
So the definition of phi really comes from part B. Can I think of that?
No, so sorry. I might not be understanding your question, but I'm assuming I'm in a setting where this happens. Okay, so there's a unique such thing up to sign. Okay, and what I'm doing in these different parts is I'm saying, well, here are different ways to measure the size of phi. You can do it directly, or you can translate phi to being a surface, or you can translate phi to being a differential form. And this one is kind of the maybe the most canonical one, but they're all size-wise similar. Okay. By the way, I should say, this thing you can also talk about similar things just for SL2Z. You can ask how big are these homomorphisms. And there's a nice paper of Goldfeld where he discusses this question. Okay? But in that case, you have a much more sort of concrete way of understanding it because you have these modular uniformizations. So our problem here, our basic problem is that we have removed ourselves from the world where you have where you have kind of real algebraic varieties to play with. Everything is purely analytic. Okay, so now what? So now let me spend some time telling you what can we prove towards the conjecture. Are there any other questions? All right, so let's look at this formula for a moment. So let's call this formula star. And I'll sort of list the difficulties you have. And so one can try to apply star. So one can analyze, let's say, the analytical behavior of the right-hand side so this question, all right, I haven't precisely defined this for you, but as the level goes to infinity, this is related to something Valentin was saying, you understand what the distribution of eigenvalues converges to very precisely. And correspondingly, it's fairly easy to understand the asymptotics of this, except for the following painful issue. Maybe you have an extremely small eigenvalue. Okay, maybe this operator has an eigenvalue very, very close to 0. And then this becomes small and there's nothing you can do about it. So as if there are no small eigenvalues, or maybe a better way of saying it is few small eigenvalues for delta 1. Okay, so the exact condition, so let's call this condition few f for few small eigenvalues. So if you go through this, you find everything is fine. You understand exactly what's going on, except for you have to drag out the small eigenvalues by hand. And when I was thinking about this, and now I still know absolutely 0 about this. Okay, absolutely nothing. So, but the nature of the statement that you need is the product. So we would need to know something like this: the sum over all eigenvalues lambda. So these are eigenvalues of this operator this Laplacian operator here. You just need to know, basically what you need to rule out is that there are a whole lot that are exponentially small in the volume, which is absurd. Okay, it's like sort of clearly will never happen. But so let's say I'm going to call V the volume of your thing we're looking at. So let's just say that we're always assuming a co-compactness, but I will comment about what we know about the non-co-compact case, but for my initial setup, let's not worry about it. What you need is for any positive delta, you take all the eigenvalues less than volume to the delta and sum their logarithms. Okay, so you're worried that there's and you scale it by v, this should go to 0. Okay, so if you think about what the limiting distribution is, you see this is very, very unlikely to fail. But it seems extremely difficult to prove. So as a toy case of the kind of issue here, you can see, ask for SL2Z. Do you have any understanding of how close the eigenvalue of a mass form can be to a quarter without actually being at a quarter? Okay, so so if you think about it, this clearly should be true, but I see no way of. Anyway, so that's one thing. So the second thing is that you need to know that R, I'll call this R for regulator. You need to know that the regulator is also growing at a sub-exponential rate. Okay. By the way, the only problem, it's very easy to bound R from below. It's not a problem. And anyway, if R was small, it would only increase this. But it's okay. So the point is that given.
So after experimental
about
of the spectrum of delta 1.
So I know Andreas Strombergs, and I talked to him about this many years ago. It's probably, but like certainly looking at that, the spectrum near 0 didn't show any peculiar behavior. That is, it behaves as you would expect from the limiting point of view, and then certainly you would, yeah. I would love to see even any much weaker. I basically know 0 about this. This is the situation here is a lot better. I'll say about it in a second. But so what do we know? Given F and R, so here's a fact. Given F and R, we get the conjecture. Okay. Now, all right, this is, so I'm going to talk, as I said, I know nothing about this. We know quite a bit about this. But still, actually what got Bergeron and I started on this was the observation that, in fact, in a closely related context, we can completely sidestep both of these at the same time, and then we get unconditional results. So let me say a bit about, so I have to change the problem slightly, and then we'll really get the analog of this conjecture. And then we'll come back to what more we can say here. So Bergeron, this is in a paper. So there's another paper of just with Nicholas Bergeron and I from a few years ago, but not with Sengun. Okay, so you see, can avoid both problems by changing the weight. All right. So now, here right. So in this board, I'll say in a sense the really unconditional things we know. So when I say changing the weight, let me go back for one moment again to SL2Z. Okay. So I'm not going to. I'll state the result, but without defining all the terms, because again I don't want to go into homology. But suppose for SL2Z, as I said, there's a pairing between this and weight 2 forms. Now suppose you want to know, as Henrik was asking about in the first lecture, well, what's the analog for higher weight? There's no analog for weight 1. Okay, weight 1, there's really nothing. But this works perfectly well for higher weight. You just have to be willing to. So for higher weight, the analogous statement is rather than this, you have to take the homology of this, the same group, with coefficients in some module. So this is a module depending on k. Okay, it's so all right, and there's the same thing is true here. The analog of changing the weight is looking at homology with coefficients in a different module. And so what we show is that, so we proved the analog of the conjecture. So for in this context, so in the context of a co-compact group in SL2C, for what we call strongly acyclic weights. And I won't say what this is, but the point is that in fact, so the weights here, in this case, the weights are parameterized by a pair of integers, and strongly acyclic means that the two integers are different. So it's actually a generic condition, not a special one. Okay. When I say the analog of the conjecture, there's a different constant, but otherwise the conjecture is exactly the same. Okay. So this is very satisfactory in the sense that from the point of view, say, of the Langlands program, there's no one weight is as good as another. So it certainly gives you pretty strong evidence for the underlying phenomenon. But in fact, so we did this for all groups. And when you do this for all groups, something very pretty happens, which I'll say. Okay, so for the exact definition of this, the exact statement, you can see our paper, but it's that type of statement with a different constant and with abelianization replaced by homology. One thing I wanted to say is that at almost the same time as our paper, Werner Mueller proved a similar statement, but at essentially the same time, but as the weight goes to infinity rather than the level. Okay, so it's sort of strange that we were, yeah.
So in this strongly acyclic case,
yeah.
So the proof is by following the same strategy.
Yes. Okay. So the strongly acyclic case, I mean, the point is, and it's a little bit surprising, is that these strongly acyclic things exist in the first place. But given that they exist, what happens? The eigenvalues are all forced to be away from 0, and R is 1. Yeah. So it's a complete surprise in a way that they exist because they don't exist for Shimura varieties. So it's not, okay. Anyway, so this is, it's interesting. I mean, as far as I know, no one is really thinking about this before, and then Mueller somehow was thinking about it at exactly the same time as we were. Let me say something about different general groups because there is something to be learned from there. So we prove a similar statement. So we means Nicolas, Berger, and I. With SL2C replaced by any group. So similar statement means exponential growth of some similar object by any group G satisfying some condition, which the rank of G minus the rank of a maximal compact subgroup is 1. And gamma ab was replaced by some higher homology group. Okay, so for some higher Q. So I'm not going to larger Q. Now, this condition here is a strange condition. Rank G minus rank K is 1. Okay, so for example, it includes the groups SL3R, SL4R, maybe SO PQ with P and Q odd, but not SLN for n bigger than 5. Bigger than or equal to 5. SLNR. Okay. So these are groups. So if you don't know what this is, it doesn't matter, but this is almost, there's only maybe one other example if I remember rightly. But so, okay, so you go through this method. The point is there's all sorts of computations to be done here depending on the group. And you find to your disappointment that you get a result of this nature only in this case. But here something wonderful happens is that according to heuristic B, so you can work through this heuristic with the non-abelian Cohen-Lenstra heuristics, which I mentioned earlier, and you find this wonderful thing that these should be the only groups, only G, with exponential growth of torsion homology. Okay, so here's where this heuristic B by itself is certainly something you should be somewhat skeptical about. But it is a very nice thing that it meshes exactly with what you can prove. So the proof, for a reason that I won't go into, but you can prove something here, and then otherwise you get nothing, and you're left wondering what happened. But fortunately, the heuristic says is that what the cases you can prove are really, I think, the only cases where you have this. So in other words, we conjecture, but we can't prove, thus, that there is no exponential growth in any other case. In the cases where rank G minus rank K is not 1. Okay. I think we can't prove is maybe not a strong. Again, this is the sort of thing about which I know 0. That is, I have no way besides completely trivial ways of giving you upper bounds, non-interesting upper bounds for the size of the sort of things we're discussing. So it's okay. So all this is under this. When I say is under this switch that you switch to a different weight where you can avoid these issues. And now I'll come back to what kind of things we can say about especially the second thing. So now we'll go back to the original question: trivial weight corresponding to abelianizing. What about in the non-co-compact case? So now so at least for SL2C. And the non-co-compact case, there's quite a bit of work, and there's work of Jonathan Pfaff and Jean Rambaud, which give now similar results in the non-compact case. By the way, the non-compact case here is really painful. Okay, it's not like it's much worse than just the horror of the trace formula. I mean, when you try to regularize this and you have a continuous spectrum, it's really, really awful. This strongly acyclic thing makes life easier, but anyway, I just want to say it's not. I put it like a small. I think the number of pages involved in this one line is probably greater than the number of all the other papers mentioned put together. So it's not. It's a substantial problem. It's an even more substantial problem to do the same thing in higher rank. Okay, and this is really, it's not just a technical problem. I've thought about this for SL3, and I really, in fact, I mean, in rank 1, at least you can work hard and sort of see how to do it, but I actually don't even see how to do this for SL3. All right, so now, what's the time? Okay, so let's talk a little bit about what we can, let's go back to the original problem, what we can say about this. Are there any questions? Yeah.
Is there absolutely anything known about F? Like, is there anything like trivial result, or is it just?
I personally know. Trivial result. One could give a bound for this. I'm not sure how big. I mean, certainly not sure it goes to 0, but you could give some bound. The point is, in this case, I mean, if, for example, in some cases, you don't even know how to give any bound on how close an eigenvalue could be to 0. Here, there's some a priori bound you can give over how close an eigenvalue could be to 0, because somehow you can switch the eigenvalue problem for a discrete problem with integer matrices, and you have a lower bound on how close the eigenvalue of an integer matrix could be to 0. So that would give you some bound, but it's totally useless. Okay, so yeah, any other questions? All right, so nothing about F, but R is better. And so today let me say a bit about the analysis, what we know about some things about the size of R, and then tomorrow I'll talk about the kind of, or whenever the next lecture is, I'll talk about the little more about. It's an algebraically interesting object. Okay, so what we want to show, so we'd like to show this, I'll just rewrite it over here, log R over, so R, the regulator, should be bounded by the exponential of epsilon times the volume. All right, so if this fails, right, if you look at, what am I saying? I'm saying that if this were to fail, it means you have this homomorphism to Z, which takes exponentially large values on small matrices, which seems absurd. So it might seem that this is something which, again, this is this might seem like something which, so to speak, you should expect, but that's not at all clear to me. So I don't know the exact current status, but I'll say that Brock and Dunfield have at least produced maybe not counterexamples to this exactly, but closely related counterexamples for non-arithmetic gamma. Okay, so they don't produce a counterexample in the exact setting where, say, Burchard and I make a conjecture, but they produce something very closely related. So it's completely possible that this is that this is always true. Is really has some special feature of arithmetic, and not a general group theoretic or geometric property. Okay. So one case. So let's study it. I'm going to say a bit more about what this. So maybe I'll just say in words. One case where we understand R well, one relatively easy case. So easy from the point of view of having a good upper bound on R. Is when all the cohomology is when all of this space, which I called all of the what did I call it? Well, let me just say when all of gamma naught n ab comes from base change, comes from Q via base change. So I'll say via a lift in the sense of Valentin's talk. When I say this, I just mean the characteristic zero part. So let's say tensor with C. Okay. All right. So I'm not going to. Without going into details, suppose you start off with M, which is an integer. Okay. And then you can also think of M as being in O. So you can sort of form the subgroup gamma naught M in SL2Z. And you can form the corresponding subgroup gamma naught M in the big in SL2O. Okay. It turns out that there is a lift that goes from the sort of free part of this to the free part of lift, which is called base change. Okay. So this is one way of producing examples where yeah, in fact, it's a fairly common. It's not at all, at least not at all uncommon that all of the free part of this comes from base change in this way. Okay, because it's sort of not here, unlike SL2Z, this free part is somehow usually small, except if explained in some way. So in that case, we can understand that we can give the correct upper bounds on the regulator. Okay, and that uses this topological interpretation part B. So here, what you do is you produce enough totally geodesic surfaces and use part B. Okay, and use part B. Now, there's a reason why we wanted to study this specific case is that for numerics on the torsion, this case actually looked pretty bad. So we were a little bit worried that this was a case that had some reason to might have some reason to believe this would fail. But in fact, we can give a rather good bound. The actual bound we get in this case is something like, so we never wrote down that we just proved it's sub-exponential, but I think what we actually proved is something that it's exponential in square root of the volume, something like this.
Can you give a criterion on M which you can check is valid for infinitely many times?
Oh, no, I can't. But so I certainly expect. So this case and the other case I'll mention, I expect them to be valid infinitely many. In the numerics we did, they were both valid, say, around half of the time. Yeah, up to the. Of course, some of these things change for very large values of M. But when I say this happens a lot, I mean I don't remember the numbers we wrote in the paper, but maybe half of the time in some range. Okay, I'll okay, so a more interesting case is when okay, let me just say next time. Okay, so I did want to say at least a few words about this Laplacian determinant. So all of next time will be devoted to studying this R in the case where you have a single form that comes from an elliptic curve that's not base change. Okay, so related to an elliptic curve over O. And what we'll see is that this conjecture then becomes related to questions of Diophantine geometry in a sort of very surprising way. All right, so in the last few minutes, I'm just going to go back to the analytic torsion formula and talk and just give you a quick, very brief flavor of what these Laplacian determinants look like. Are there any questions? All right, so I was planning to, I would have liked to spend more time on this Laplacian determinant thing, but it's probably the least number theoretic part of it. So I'll just, so how do we define this sort of determinant of delta? Okay, I'm going to, as I said, I prefer this way rather than the Selberg zeta function because this way it's easier to understand this effect of small eigenvalues. Okay, you can really see if there's a small eigenvalue, it causes a problem. But the definition actually makes sense for any makes sense for the Laplacian operator on any compact Riemannian manifold. And I will again, this definition is due to Ray and Singer. They introduced it for the purpose of stating their formula. And so what do you do? So you have the eigenvalues be the eigenvalues. And a basic fact true in this context is that the function sum, so let's call it z of s, sum over I bigger than or equal to 1, lambda I to the minus s. So Weyl's law tells you that this is convergent when the real part of S is large, and it actually has an analytic continuation to the complex plane. Analytic, meromorphic, sorry, meromorphic. And you understand exactly where its poles are, and so on. So this result is obtained by, it's not very hard, it is obtained by taking the Mellon transform of things we know about the heat kernel. But anyway, it's true for any Riemannian manifold. Now, formally, so ignoring issues of, well, okay, so in the region of convergence, the region of convergence, if you differentiate this with respect to s, what you get is negative log lambda I over lambda I to the s. So sort of formally, if you put s equals 0, so I'll put this in quotes, log of lambda I is equal to, in quotes, the negative of the derivative of this is 0 sum. If you just formally put s as 0. And this is what we take as our definition. Okay, so we define the determinant of the Laplacian to be the exponential of minus z prime at 0. Okay, that's the definition, and it works for any compact Riemannian manifold. All right. So let me just do, to give you a flavor, I'll just do a single example, and then we'll stop. Are there any questions about the definition?
Does this thing have a functional equation?
No, that's not. No. Yeah, this has no it has no sort of none of the other algebraics. It just has a meromorphic continuation, and it's a soft fact. Yeah. All right, so let's do the example when M is a flat torus. So R2 mod Z2 with the usual metric. So it looks like this, okay, with periodic boundary conditions. And the Laplacian operator is minus dxx minus dyyy. And so this example, it's kind of a special example, but we'll learn a little bit by doing it. The eigenfunctions are e to the 2 pi I nx, e to the 2 pi I my, and the eigenvalue is 2 pi squared n squared plus m squared. Okay. So in other words, this function, the n and m are integers. So the z of s is, all right, I'm going to forget it. I'm going to lose the 2 pi just so I'll almost certainly screw something up if I keep it in. So this function z of s looks like this. So in other words, it's a value of an Eisenstein series. This is an Eisenstein series for SL2z evaluated at the point I. Okay, so at the point I. All right, so to do this computation, we can actually compute this absolutely explicitly. And so I'll very briefly do it. So more generally, we can look at let's do it for so what we want, right, is we want to compute the exponential or minus z prime at 0. Okay, but let's do something more general. So we will compute this, but we'll do it by computing it for all lattices at once. So we look at ES, which is the sum of y to the s. This is the standard Eisenstein series for SL2z. All right, so we can recover this. Look at on the upper half plane mod SL2z. This is the standard Eisenstein series. And so our function we want is the value of this at I. Now, all right, so what we want is to differentiate it at 0. Okay? It turns out you can do this basically by pure thought. So this Eisenstein series satisfies two properties. It's an eigenfunction, and its constant term is y to the s plus c of 2s minus 1 over c of 2s y to the 1 minus s, okay, where this is the completed zeta function. So now if we want to work out the derivative d by ds es at s equals 0, let's call this function capital F, you learn something about this from both of these facts. The first thing you learn is that the Laplacian of f is equal to 1. Oh, sorry. This is not actually an equality. OK, it's this plus decaying. OK. So when you this function differentiated at 0, it gets something a Laplacian 1. And the second thing says that f is equal to y, no, differentiated, log y minus pi y over 3 plus decaying terms. OK, so if you differentiate this, that's, and you evaluate the zeta, the pi over 3 comes from a zeta of 2. So what this says, all right, so I claim that in fact this function f is the logarithm of y times delta to the 1 over something, 6. OK, where delta is this modular form of weight 12. OK? And the reason I know this at this point is that these two functions, the difference of these functions is now a harmonic function which is going to 0 at infinity. So it has to be 0. OK? So in other words, what we've done, so in the end, if you go back to this exp of minus z prime at 0, it's something like this y times delta to the 1/6. Maybe I might have missed an inverse. I'm not sure if there should be an inverse or not, but let me put -1. OK. So so this is certainly a very striking calculation because it shows this invariant in this simple case gives you a number theoretically interesting thing. And I think that was, I mean, Ray and Singer did this computation. I think it certainly suggested to them it was a good definition. But actually, the important thing to learn from this computation is that this Laplacian, what did I do? This Laplacian thing, this series itself, I evaluated this at a specific point by looking at it as a function on the whole space. OK, and then I used harmonicity. And that's the sort of moral of the story is that these Laplacian determinants are very difficult to understand themselves, but you can understand how they vary. OK, you can differentiate them when you change parameters. And just to finish, so one of the reasons that Ray and Singer realized that they were onto a good thing is that the right-hand side of their formula, the right-hand side of this Ray-Singer formula, which involves the determinants, what they did is they said, well, here's something which depends on a metric. And then they changed the metric and they watched what happens, and they found it to be metric independent. All right, so it's very hard to understand those directly, but they could check that it doesn't change as you change the metric. So if you have such an invariant of a manifold with metric, which is then independent of the metric, it's reasonable to think that it's something purely topological. OK, so that's the one. The takeaway from this is not the specific example, but that you can understand how this Laplacian determinant varies when you change things. So sorry, I went a little bit over time.
Are there any questions? Yes?
I'm just a bit confused about your last formula. So you take the limit as z tends to 0 or something? I see no y on the left hand side of x of z prime.
Sorry, where?
X of minus z prime of 0?
Yeah, there's a y, but it doesn't have a y at the beginning. You see, that's what he's saying.
There's a y.
Y equals 1.
Oh yeah, I'm sorry. That's right. I should specialize this to the point I. That's right. Sorry. Thank you. So the y should be 1. You're right.
Any other question? Okay, thank you again.
Actually, usually when I have given this type of lecture series, the attendance goes something like this. So I'm happy that this time it's more like this. Okay. So I'll remind you what today I'll just talk about regulators. So let me spend the first few minutes just recalling the story from last week, and then we'll talk about the regulators. So from last week, our situation was we had these subgroups gamma naught of n inside SL2 of an imaginary quadratic field. Okay, and the okay, so this is matrices where n divides C, but now remember everything, all the coefficients and n lie inside this ring here, and the conjecture that we were discussing is that when you take the abelianization of this, and you just take the finite part, so it might have some infinite part, and you scale it by the volume, that this has a definite limit, which is 1 over 6 pi. Okay, so what I said last week are the main tool in trying to understand this from an analytic standpoint. So I described some heuristics, but the main tool is this story of analytic torsion, and in particular the following formula. So the statement that I'm about to write is literally true only in the non-compact case. The size of this multiplied by a regulator, which I'll divided by the volume, is equal to some ratio, something to do with determinants of Laplacians. Okay, so all right, so what I said in the previous lecture was, firstly, if you allow to pass to a kind of, if you switch this for a different weight, this is the analog of weight 2. If you go to some different weights, we can prove the analog of this conjecture. But for this conjecture, so using this analytic torsion formula, one can prove the conjecture in the non-compact, or at least in the compact case, at least, and as I said, this now it's close to being proved in the non-compact case also. One could prove that if we know two things. Okay, the first, few small eigenvalues. So you can understand this object rather well as long as modulo the issue that this delta 1 might have some eigenvalues very close to 0. So delta 1 has few small eigenvalues, and I wrote the precise meaning of that last week, so I won't write this again. This is something we certainly heuristically we strongly expect to be true, but this is totally, I have nothing to say about it. Okay, I don't know how to prove anything. But the second thing, which I'll call R, is that you need to know, so once you understand the right-hand side is large, and you can understand exactly how large, you need to know that that size comes from this finite group and not from R. So you need to know that log R scaled by the volume goes to 0. Okay, so I discussed, let me give you the definition of R once more. And then we'll... So this is what I'll talk about today, and in particular I'll say more about what the actual... So what is interesting about this R is not just it's trying to prove this, but it's actually a very interesting invariant. Okay, that is, it's related to many other objects of number theory, including L functions. Right, so here's the definition of R. And maybe I'll write it down here. So the definition of R. And I will just define it in the case when the free part has rank 1. Otherwise, it's a similar definition with determinants. When okay, so I said this last week, but I'll remind you. So there's a pairing. You have, just as in the case of the thing I said at the very start of these lectures about classical holomorphic forms, there's a pairing between this and a space of modular forms. Okay, so I've written it S2 to be suggestive, so it kind of reminds you of the case of classical modular forms. But here, in our context, this is the space of harmonic 1 forms. On this gamma naught n mod h3. Okay, if you make the same definition in the case of the upper half plane, the harmonic 1 forms are sums of holomorphic forms and their conjugates, f of z dz and its conjugate. So this is really an exact analog here of the space of holomorphic weight 2 forms. And this pairing is given by the same formula as in the first lecture. So that is, if you want to pair gamma and a form which I'll call omega, you integrate omega on any path between w and gamma w for any w in H3. Okay, so still not done. All right, so now this. Yeah, by the way, let's, at some point in this lecture, I'm going to switch to the non-compact case. But here, let me make the statements in the compact case. One has to slightly modify them for Eisenstein series. So what do we do? So we can integrally normalize an element of omega in this S2 of n by requiring that, all right, so I'll write it gamma, what shall I call it? Gamma naught omega to be 1, where gamma naught n projects to a generator of z. Okay, so in general, if you have, so you should think of this as a space of modular forms. We have different ways to normalize a modular form. Okay, so for analytic purposes, the two common normalizations that one sees, if you think about holomorphic forms, is you can normalize the L2 norm to be 1, or you can normalize the first Fourier coefficient to be 1. Okay? But in the context we're discussing, this is an equally natural normalization. You require that when you integrate it against these cycles that you get 1 on a generator for this. Okay, and once you've done that, then you define this regulator to be omega inner product. So maybe I should call this, I should just have a notation for this. I'll call it omega subscript z to suggest this is a integral normalization. Okay. All right. So now let me. Okay, that's the so this I think up to here were all things I said last week, and now I'll try to say something about the nature of this. Of this thing. Are there any questions? All right. So the only. Okay. So now I'm going to state a result from this paper with Bergeron and Haluk Sengun. So a result from. So after I state the result. I'll say a bit later about the proof, but the main thing I'll try to communicate is what the difficulty here. Okay, it's not maybe a difficulty one is so familiar with in the analytic theory of modular form. The difficulty is trying to, so to speak, find such an element. Okay, so in other words, this pairing is not so hard to compute. But if I just take an element, you really have no idea where it projects to in here. Okay, you could have an element of very modest size, write down a physical matrix here, very modest size, but yet its image here is very large. Okay, and that's the basic problem which one faces when you're trying to bound this from above. But this result is actually, in a way, more algebraically suggestive than analytically. So suppose now this really depends on, suppose that. So we're really in the non-compact case. Okay, so in other words, that means at various points I should put in the word cusp forms rather than all forms, but that's all. But this is important, and you'll see why it's important. Okay, now, according to, so the Langland's program predicts. Okay, so yeah, I should have said, in this setting that we are, where this is Z plus a finite group, maybe it was implicit in this, but this is one-dimensional. Okay, this has just one copy of Z, it's just a one-dimensional complex vector space. Okay, so there's just one, this really pins this down. Now, if you were in a setting in classical modular forms where the space of weight 2 forms is 1, then there's an elliptic curve associated to it. Okay. This happens the first time it happens is at level 11 over Q, and then it's associated to an elliptic curve. So the same thing is predicted, although not proven here. So Langland's predicts that associated to this modular form. By the way, actually, I said it's a harmonic one form, but if you write out what that means, it means it's the mass form of a certain eigenvalue and weight. Okay? So associated to this, there is an elliptic curve E over the field we're dealing with, Q squared minus D, of conductor N and various other properties, a matching between Hecke eigenvalues of this and point counts on this. So I'll just say same condition as over Q. Okay, so if you look up the story for weight 2 forms over Q, it's exactly the same. Now I should say this statement is actually not, there's a subtlety which happens over an imaginary quadratic field, which is that even when the dimension of the space is, so over Q, for example, when the dimension of the space of modular forms is 2, you might not have 2 elliptic curves, but you could have this could come from an abelian surface. In this setting, something similar can happen even if the dimension is 1. This can come from an abelian surface with quaternionic multiplication, which is sometimes called a fake elliptic curve. So I'll just ignore that, but I think exactly the same result should hold with the same proof in that setting. Okay, so Langland's predicts this. So we will suppose this to be so, is true, and also assume the Birch, Swinnerton, and Dyer conjecture for E and its twists. Okay, when I get to it, I'll say exactly, but this is then this regulator R divides. All right, so there's an explicit fudge factor, which I want. So let me just call it M. I'll say time. The more important part of it is omega E to the minus 2. So this is some explicit fudge factor, explicit and involving only the torsion on the elliptic curve and the level n, and also actually the adjoint the adjoint L value of this modular form. But this is the part which is interesting. This is the area of the fundamental parallelogram for E. Okay, so in other words, what you can do, you can take this elliptic curve and you take its complex points and you can integrate over it. You take an integrally normalized one form, wedge its conjugate. Okay, so the absolute value of this. If this doesn't have class number 1, there's a slight issue in defining this. But again, I'll skip over that for simplicity. Okay, now, so what I want to, so in fact, I think that there should be an equality of this form. So let's say I think that this is really an equality. So R, it should be equal to some essentially explicit factor times this. Okay, the proof says it divides it, but I think in truth it's an equality. Now, and let me say that another way to make it, to try to say why this is an interesting thing. This omega e to the minus 1 is essentially the Falting's height of the elliptic curve of E. Okay? So in other words, if you write out explicitly an equation, if you write explicitly an equation as E is a minimal equation, which is y, which if E is given by this, then this is going to be approximately, I'll say what that means in 1 second, it will measure the size of these coefficients. Okay, I hope I got the powers right. Good. This approximate sign means it's not that they are, it means the logarithm of the two sides is the ratio of the logarithms goes to 1 when something goes to infinity. So, well, in other words, if so, this statement, okay, what it says. So this thing here is some measure of the height of E. So it's a measure of the arithmetic complexity of E. And this thing, as I said, it measures the complexity of the modular form associated to E. Modular form associated to E. So at least it came as a great surprise for me that these two things might be the same. I mean, of course, they both measure complexity of something, but the nature of them is so different that I can sort of, as you see, the proof will be sort of very computational, so it doesn't really explain why such a thing should be true. Moreover, I think that a statement of this form might be true more generally. Okay, that is to say that the complexity of in some normalized sense, such as Falting's height of a variety, should have something to do with this analog of regulator of the associated modular form. But that's very speculative. So, okay. Anyway, so this is the as I said. What's interesting about the statement is this relation between R and the height of the elliptic curve. Now let's see what that does for us in the context of our wanting to bound it. Okay. So the point is that. So to prove that, so to show that log R over the volume goes to 0 in this case, then you need only to show that the size of the coefficients of this elliptic curve are bounded I mean, on a logarithmic scale, basically, by the level. And this is a standard conjecture of Diophantine geometry, the size of coefficients of elliptic curves bounded by the level. So this follows from many standard conjectures. For example, the ABC or the Frey-Spiro conjecture. These conjectures are much stronger than this. Okay, these conjectures are about polynomial bounds. We only want bounds at a much, much weaker scale. But anyway, the point is that yeah, so in this way that this gives, at least assuming BSD and sort of very safe Diophantine estimates, okay, I mean far weaker than what we actually believe. This implies that the regulator is indeed implies this slow growth of the regulator. All right, so I'll talk about where the proof of this comes from. I wanted to first have a little aside about this type of regulator in some slightly different context. But are there any questions about this? Yeah.
Are these all integers or?
What? No, nothing is an integer. These are all transcendental. I mean, presumably.
When you say R divides, you mean?
Yes, when I say R divide, good question. Yeah, I mean that R is just divided by an integer. Yeah. Yeah, you'll also see where that integer comes from and why it really should be 1. But certainly the proof doesn't say this.
And you use the full form of BSD?
I use the full form of BSD, and in fact I use, when I say BSD for E plus twists, right? So I use something that's actually surprisingly not written in the literature anywhere, which is that if you take an elliptic curve and you twist it by a Dirichlet character, you need a form of BSD for this. Okay, and anyway, so that's what's being used. Not just quadratic twists, but all twists.
Why everything in non-compact case?
Yeah, I'll also explain that. Yeah. In fact, so I don't know how to prove this in the compact case. Okay, in the compact case, let us say you make the same assumption. All you get is that R is a rational multiple of the same thing. Okay, so we're going to use the non-compactness in some essential way for the proof. Well, I might as well say we're going to make some use of modular symbols. Okay, and you don't have that. So I would love to have such a statement in the compact case, even. Yeah. Any other questions? All right, I'm going to have. Oh, well, I don't know if this is. All right, I was going to make a slight aside about how this relates to some problems related to K2, but maybe I'll try to sketch what goes into this kind of thing, and then we'll come back to that. So I'm going to sketch some ideas of proof, and this will sort of show how well. All right. So the basic point is you need in some way, of course, to be able to evaluate this pairing. Okay? So there needs to be some class of examples where you can evaluate this. So let's call omega well, let's call plane omega the L2 normalized form. Okay, so its inner product with itself is 1. So this is not going to be, right, so what we're going to try to see is how to adjust it to get this. So so suppose we can produce some element delta in gamma naught n for which we can evaluate this pairing such that we can explicitly evaluate and by that, this will mean in practice in terms of L functions. Okay, that's the meaning of explicit. Evaluate omega. Which way did I write it? Delta first. Okay, delta omega. So somehow we can explicitly work this out. Let's call it E. So this will be in practice something to do with L functions. Right. So now this delta. So let delta in. So you can take this and you can send it to this gamma naught ab, which is, as I said, z plus something finite. And so let's say it goes to q times the generator. Okay, so let's say delta goes to q in this variable, and the finite part doesn't matter at all when we're doing this type of computation. The integrals against differential forms annihilate that. Okay, so there's no, so delta, so q, i.e., okay, so delta is sent to q times the generator. So then what this says, in other words, is that, so this is q times the generator, omega over e is 1. Or in other words, this tells you what the integrally normalized form is. Omega z you get by q times omega over e. Okay, so when you're in this position, once you've explicitly evaluated just one value of the symbol, you can understand what this integrally normalized form is. By the way, I should say this is related to the aside that I'll try to get to at the end. This story works very generally, okay? That is, in the setting of the cohomology of arithmetic groups, you can always ask about this kind of, you can always integrally normalize forms. And it's always actually very subtle. Okay, it's very difficult to, this integral structure is very interesting and very subtle. Okay, anyway, that's this is the integrally normalized form, and so the regulator R is going to be the inner product of this with itself, which is q squared over e squared, and the entire problem will be that we can't bind, is that we cannot bound q. Okay. When I say we cannot bound q, of course, I don't mean it in some, in typical, it's more like you can give some naive bound which is of enormous size, let's say. So you need some. Okay, so let me explain, for example, how you can try to do this in the co-compact case. Okay, as we'll see in the I don't know how to solve this issue in the co-compact case. So there'll be no full answer at the end of this, but it will just show how do you explicitly. So next thing I'll discuss is how to produce such delta. Okay, how do we have anything for which we can explicitly compute this? Let me write on that one. Okay, are there any questions?
So do you need facially that the free part is one dimension?
No. I'm just saying that so we don't have to write determinants. If the free part is enormous dimensional, then you run into another issue. If the free part is as large as the volume, so let's say when you make this estimate, you would have another problem if the free part is of dimension that's very close to the full volume. But other than that, if it's significantly smaller, it's no problem. Yeah. Any other questions?
Do we have some a priori bound for the free part?
Okay. Yeah. On the free part, here's what we know. Just from topology, for example, you know that it's bounded linearly in the volume. If you think a little bit more, you can bound it by something which grows slower than the volume, like volume over the logarithm of the volume. There are two kind of very interesting papers, one by Caligari and Emerton and one by Simon Marshall, where they give some specific instances where they can do better. But by and large, we don't have a robust way of showing. So, oh, by the way, I mean, certainly in terms of what should be true, away from in this setting, the free part, the dimension of the free part should grow as a power of the volume less than 1. But we lack very general ways of showing that.
Yeah, I just had a question. Is finding this delta, is this in any sense, shape, or form analogous to when people are trying to do like explicit Paget type formulas?
Yeah.
Listed L functions. Any sort of an analogy?
Yeah, no, it is. In fact, I'll say it's from this. You find delta by the Walsh-Paget formula. But in fact, I mean, not just Walsh-Paget himself, that was his application, one of his applications in his original paper for his formula was exactly in this setting to understand this up to a rational number. Okay, so the story I'm about to say is not, it's going to be the Walsh-Paget formula, but it was in fact already proved by Walsh-Paget in the same paper where he shows that formula. So so as you've asked, the way one does this, okay, this is not the main, as I said, the main problem will come later when we discuss how to bound Q. But in terms of just producing such delta, the answer is given by the Walsh-Paget formula, which I think Philippe mentioned now at the end of his talk. So it says, if pi is an automorphic representation for GL2 over this field k is q squared minus d, and L is a quadratic extension of k, then this and phi is a vector in the space of pi, then Walsh-Paget in his paper he gives an explicit formula for this, okay? And in fact he gives a formula for any vector at all. It's very beautiful, but anyway, what is important for us is that up to some fudge factors, what we get is the central L function of pi times the central L function of pi twisted by the quadratic character associated. So this is the quadratic Dirichlet character associated to L over k. Yeah. Okay. Now all I'll say is what happens when you make this work out explicitly what this says, it exactly computes some value of this pairing. Okay. So in our case, we take pi to be the automorphic representation associated to this, to omega, and we'll take phi to be the vector in pi that corresponds to corresponding to omega. Be a bit careful about this, but corresponding to omega. And then if you work out what this says, you have an integral over this adelic space, but when you project, so the projection of this to gamma naught n mod h3 is a union of geodesics, is a finite union of closed geodesics. So let's say, let's call this direct union of GI. Okay, so let me just write out what geodesics look like. Okay, so each of these closed geodesics, this is just a computation. Okay, you just have to unwind the adels, you project it down to here, and you'll see this. Each geodesic GI arises from some hyperbolic element from hyperbolic element gamma and gamma naught n in the following way. So you take, so we're in hyperbolic 3 space, but this gamma fixes, so alpha and beta kind of fixes, it's exactly the same as if you know this story for the upper half plane, it's the same story. Gamma fixes 2 points on this plane at the bottom. You join them by a semicircle, And what happens is gamma kind of moves you along the semicircle. So if you take a point W here and you keep applying gamma to it, it moves you further and further along. Okay, and the way you get this geodesic GI is you just project this path, the piece from W to gamma IW. You take this piece and you project it to this quotient. Okay, so in other words, you just take one of these, this piece here, and you project it to the quotient. And if you took any other such piece, you would get the same closed geodesic. So if you okay, so in other words, when you integrate the form form omega over GI, that's exactly the same as this pair. By definition, that's the same as what you get when you pair it with omega. Okay, so the GI, the definition of that pairing is exactly, so this is true. And so then what Walsh-Bourget's formula says, what it translates to, is that you add up all of these over all the geodesics, sum over I of these pairings, and you square it. Well, in this case, it'll actually work out to be real. So you just square it, and you get L of, up to these fudge factors, L of 1/2 pi, L of 1/2 pi times this quadratic character. Okay? So in other words, this gives you an explicit evaluation. So this, you can think of this as being pairing the sum, how do you say, let's say the product of all the gamma I, gamma 1 up to. So this is an explicit formula. Okay, so this is how you produce explicit things for which you can compute that. And as I said, this was already done by Walsh-Bourget. Okay, so he to deduce statements, what he showed using that was he showed that the different L values for different twists are related by rational numbers. Okay. So this, now, by the way, you also need to do something a little bit. If L 1/2 of pi is 0, this is useless to you. But you can always find a quadratic twist with non-vanishing central value. So, so this allows one to compute this regulator up to rational numbers in terms of L values. Okay. But in either the compact or non-compact case. Okay, but this is useless for us. I mean, at least it does tell you that this regulator is something interesting because it has the same sort of, its algebraic properties are the same as the central values of these L functions. But for us, the entire subtlety is the integral story. That is, how do you bound this Q? Okay. So, and I don't know how to bound. So let me say, I don't know how to say anything more. In the compact case. Which is very problematic.
You mean because you don't have a Shimura structure? I mean, I think of Prasanna's paper.
Yeah, but so, yeah. But even Prasanna's papers are really use something, right? They like, you find many imaginary quadratic fields with, yeah. Oh yeah, no, that's right. That's right. No, that's right. As Philippe says, maybe I'll just restate what there are similar problems even in more algebraic settings, and even there, it's very far from obvious what happens. Okay, this. So, yeah, Philippe mentioned this thesis of Karthik Prasanna, which is dealing with quaternion algebras over Q, and already there these questions are difficult. Here it's much worse because nothing is algebraic. All right, so now what can we say in the non-compact case? Here we have available, fortunately, this trick of modular symbols. Yeah, are there any other questions? So here what we can do, evaluate any pairing. Oh, so let's actually take, so let's choose, we'll just choose an element in gamma naught n which projects to a generator of z, 1 in z. Okay, so over in that notation over there, so Q is 1. Okay. So in other words, the regulator will be given by, if you look at that formula over there, is just 1 over this pairing delta with omega squared. All right, now here we have the following thing we can do. So to evaluate which is the integral from w to gamma w of omega, you can take this point w to infinity. Okay, so this idea goes back at least to Manin. Okay, you can choose any point w in this, and as long as omega comes from a cusp form, so it decays rapidly, you can replace this integral. So what happens when w goes to infinity? So w is going off to infinity, gamma w is down here, and this becomes a geodesic. You can take this to be a geodesic, so i.e. you can integrate omega over a geodesic path from infinity. All right. So we'll write this in terms of L functions, and there'll still be a problem there, which I'll discuss. Okay, so this alone doesn't. These in terms of you can see this as the special case, in fact, of this Walsh-Bechet formula, where you take L to be the split quadratic extension. Okay, so this, but these have another feature which will be useful later. All right, so let me discuss what these integrals look like. So just to keep it more familiar, I'll discuss the analogous story for the upper half plane. Okay, everything works exactly the same. So for familiarity, we'll compute the analogous story for the upper half plane. Okay, so it really works out exactly the same, but if I were to write it out here, here I can write explicit Fourier expansions where here would have a Bessel function and so on. So imagine you have a weight 2 cusp form. And this element delta, let's say, is A, B, C, D. And what do you want to do? You join infinity. So delta applied to infinity is the point A over C. So you join infinity to A over C, and you want to integrate f of z dz over this. Okay? Over this path. Okay? All right, and again, this will be easy enough to do, but the issue, there'll be an integrality problem which we have to handle. So how do we do this? Let me first take a very simple case. So if, let's say A over C is actually 0. Okay, so maybe if A were actually 0, how do we compute this? Then so if we just, okay, so let's write the Fourier expansion of this, sum of an q to the n. And what we have is just integral from infinity to 0, sum of an e to the minus 2 pi ny dy. And this just gives you 1 over 2 pi times the central L function. Okay, now the central L function, so let me see, let me now, oh, where did it go? Maybe it's gone. Okay, of course, this so if we are actually in this case that you get the central L function, then you can apply Birch-Swinnerton and Dyer. And Birch-Swinnerton and Dyer says the central value of the L function so let me just ignore the 1 over 2 pi. It's a product of several factors, the Tate-Shafarevich group of the elliptic curve, a Tamagawa number divided by the torsion part squared times a period. In the imaginary quadratic case, it's this complex area. Okay. So in this unrealistically simple case where A over C works out to 0, i.e. in this case we would get this pairing works out to be this, so some integer which comes from the size of a Tate-Shafarevich group divided by size of torsion squared times omega e, and then this regulator comes out to be the reciprocal of this, so e torsion to the 4th times omega e to the minus 2. Maybe I should keep this as modulo some integer. Okay, so that's the nature of the statement I made. The regulator, it divides. Okay, you don't know what this integer is, but anyway, the regulator divides a fudge factor, which is this size of the torsion group, which can be very easily bounded, times this. This is the interesting part. This thing is the height of the elliptic curve. Falting's height of E. Okay, this, however, so that's the way this argument is meant to work, but the analog of this essentially never happens. Okay, so if A over C is not 0, then you have to do something more complicated. Okay, your entire worry is in fact that, okay, I chose an element delta projecting to 1, and the entire worry is that this element delta is extremely complicated. Okay, so your worry is in fact this A over C has some very large height. So in that case, okay. Oops. Is that okay? Yeah. Okay, but so if A over C, if you're not so lucky, what happens? Then you can still write this as a combination of L functions. So we have no other source of understanding of the integral properties of things besides Birch-Swinnerton and Dyer. Okay? So if you don't have something like Birch-Swinnerton and Dyer, you are completely lost in this. Okay, so we need to go through L functions because when you talk about modular curves, you can make direct arguments sometimes using algebraic geometry. Right? Here, there's nothing. There's no algebraic structure. So everything must be reduced to L functions because there's no other way, no other handle we have. So what happens here, the integral from infinity to A over C f of z dz is now sum over n. Similar thing. If you work this out, you get 1 over 2 pi. And this is what the sum I write is in the sense of analytic continuation. But then you have this factor e to the 2 pi I a n over c. So this is not an L function, but you can write it as, so this can be written as some linear combination. So Fourier analysis, you can rewrite this in terms of Dirichlet characters. So you can written as a linear combination of things like L of 1/2 f times chi, where chi is a Dirichlet character of conductor dividing. So this is sort of a sum. A chi is a Dirichlet character of conductor dividing C. Okay. Right. Now, you can hope to now do the same thing. You can apply Birch-Swinnerton and Dyer to understand the kind of integral properties of this. Now you have another problem. The A chi's are not integral. Okay? And in fact, up to here, you can kind of make analogs of this kind of story also in the compact case. But you run into a similar problem. These A chi's are not integral because when you write out this, for example, if C is prime, hopefully I'll get this right, and when you do some expansion of this, you get a sum over chi. You get Gauss sums. It looks something like this. But you'll divide by C minus 1, which comes from when you do Fourier analysis. Okay, if n is non-zero mod C, you have something like this. So you get a denominator. So you get denominators related to C. And this is, again, okay, so okay. But now what you can do is, so this is where the sort of integral difficulty ends up, these denominators. But now you can play the following game. So to avoid these denominators, you take your original delta, rewrite delta, you take this delta and you write it as a product of two other elements. Okay, so delta omega is delta 1 omega plus delta 2 omega. Okay? And if you can play exactly the same game for these, and what you find if you do it carefully is you can get a different set of denominators for the right-hand side. Okay, so can arrange to get different denominators. On the right-hand side. And then so thus these denominators which potentially occurred here couldn't actually occur in the first place. Okay, so just this final, there's a similar story in the compact case, but the denominators become related to class numbers, and I don't know how to play this kind of game effectively. Okay, so this last step is the point where you kind of avoided that you kind of win something. Okay, so that concludes the. So what have I done to here? So right, so regulator divides some explicit multiple, some explicit, and some explicit times omega e to the minus 2. Okay, as you saw, this explicit thing really just came from the torsion, the size of the torsion of the elliptic curve. So let me just say one word about why you would expect this to be an equality. Okay, the failure of this to be an equality comes from this integer. Okay, that integer, if you trace back, is the Tate-Shafarevich group of this elliptic curve. Okay, now the sort of thing which would need to happen for this to be if this weren't equal, is that you would need to have not just the Tate-Shafarevich group be non-trivial, but there'd be some prime that divides all the orders of all the Tate-Shafarevich groups of all twists. Okay, so this kind of thing although it's very hard to prove, there are conjectures of Kolyvagin and others suggesting that kind of phenomenon should never happen. Okay, so let's say to show equality, would need to know. Another way to say it is something like non-vanishing mod P results. Okay, so which you could think of either as being about the Tate-Schaffner image group or being about the L function. Okay, but I do think, for that reason, I think this is really an equality. And yeah, I'll say one more time. I think this general phenomena, this might be a general phenomena. These regulators are related to heights, and if so, that's quite, as I said, it's quite interesting because somehow the two sides are of different natures. Okay, so maybe I stop there. Questions?
Could you give just a hint of the idea of how you do when the free part is Z2, for instance?
Is what?
Is Z2 when you have Z2 instead of Z?
Oh, actually, to tell you the truth, I never wrote it down. So you can run this argument, so to speak. Let's say there are two elliptic curves that contribute to it. You can run this argument for each one individually. Now, then there'll be another factor about congruences between those two forms, which I think should. So if which I think you can bound in some explicit way in that case. I've never. So in other words, I've never written down this argument. I don't think there are any problems when it has bounded dimension. That is, you analyze it form by form, but you have some subtlety because the integral structure doesn't break up form by form. But nonetheless, I think it's easy to bound. I say that without having thought through it very carefully. When the rank of the free part, yeah, when it starts to, I guess it seems to me it should be fine even if the rank of the free part was, as long as it's sort of volume to a power less than 1, but I haven't really thought very carefully about the estimates for that. Yeah.
So when you say you have a so this issue of eliminating the denominator is related to class number problems?
Not really.
No, you said this.
Oh, I see. Yes. So yeah, for example, in Prasanna's paper, it's Prasanna's thesis, right? He does when you do an analog of this, where in the Walsh-Burget context, when you do Fourier analysis on this kind of, basically you end up doing Fourier analysis on class groups, and then you end up dividing by class numbers.
Okay.
Yeah.
But I mean, you may have, so when you say class groups, it would be class groups of full rings of full quadratic rings, so maximal.
No, you lose, you don't have much control over things like that. Okay. Like, for example, here, there's this element, where did I call it, delta. Now this, which generates, I've lost it, but you pick an element which corresponds to a generator, you don't have much control whether it corresponds to a maximal quadratic ring or not.
Okay, but if we were non-maximal, you would have more leverage in a sense. So.
I'm not really sure. I don't. I don't know.
So is that possible that then you can translate your delta by some sort of Leckie operator to make it non, so if you suppose it is primitive and it becomes less primitive, but then you are...
I haven't had much success with such a thing, but I don't know if, I don't know.
Because this A over C looks like just non-primitive quadratic rings over the split quadratic algebra of relativity.
Yeah, but see, what was important here in a way is that you could bound this C minus 1, you can think of it as coming from a class number of a degenerate quadratic ring. And it is important in this denominator avoidance argument that you have such an explicit understanding of those.
But so then my question would be to move the delta, try to move the delta to be in such a situation by some big amount. I don't know.
Yeah, no, okay, I don't know how to. I've had very little success besides this argument in doing anything.
Any other question?
Yeah.
To bound R, why do you exactly need the equality? Why not just integer time of that thing is enough?
I'm sorry.
The R, the value of R, it says integer times the fudge factor times omega e.
R divides this.
Yeah, I mean, why do you need it? Why do you need exact equality?
You don't. Like, this is enough to bound it. Yeah, because R is just divided by an integer, so it's less than this. So this is fine for the purpose of bounding, but I would like to know what's true, and I think it actually should be equality. Yeah, but for the strictly speaking, for the application, this is fine. Yeah.
Yeah.
Do you know of any GL1 incarnation of this
Oh,
quality?
which this?
Yeah.
No, it already has interesting incarnation for GL2 over Q, but I don't know for GL1. I think it really might not have. I can explain why to you afterward, because GL1 is abelian. I think it's.
So if there is no more questions, so thank you.